Thank you very much for attending the Generative AI Summit, the second stage. Let's see. So, as a quick reminder for everyone, there's a super early bird discount for ODSC West that will be ending this Friday. So please check it out when you have the time. So, our first session for today will be the MLOps stack in a Gen AI world. Thank you very much for joining this. And as a quick reminder, a brief survey will follow the end of the session. All of your feedback helps us shape future conferences. So please join me in welcoming, Yuval Fernbach, co-founder and CTO at QWAK.
Hi, everyone, and thanks for joining this session. In this session, we'll talk about MLOps and how it's related to Gen AI. Basically, why you still need MLOps to make sure that your Gen AI models actually impact your business, impact your product. So I'm Yuval Fernbach. I'm a co-founder and CTO at QWAK. QWAK is a machine learning platform, and in this session, we won't talk about QWAK itself, but we'll talk about some of the best practices and how we are seeing our customers actually implementing and making sure that their Gen AI models actually impact their business and their product. Before founding QWAK, I was a machine learning specialist at Amazon Web Services, and before that, I was the CTO of Mamram, the IT department of the IDF. So just a bit about the agenda for today. We'll start by talking a bit about Gen AI models versus regular models. We'll talk about what are the differences between them two, why there is a specific conference about Gen AI models, why many companies actually see how Gen AI can impact their business, and if it's really different than regular models. Next in the agenda, we'll talk about some of the closed source commercial products for Gen AI versus the open source ones, in which cases a company should choose a commercial closed source product, in which cases it makes more sense to use an open source product. We'll talk about these two options, the advantages and disadvantages of each one of them, and try to have a better understanding on in which cases you should choose which. And the third part of the agenda will be specific about MLOps. We'll talk about how can you create a Gen AI model pipeline. When do you need to create such a one? What are the advantages of creating it? And I will share a simple architecture of some of our customers actually doing it. So let's start the agenda with Gen AI models, and basically what are the differences between Gen AI models to regular models. So I do want to start by saying that generative models are a class of machine learning models. It's eventually a machine learning models. It's any type of machine learning model can be built, trained, and deployed. And one part, of course, one class is generative models. And the biggest differences between generative models and machine learning models is that basically the outcome of these models. So the outcome for generative models is to generate new data based on the data that they were trained on. For example, generative text. So models like, for example, GPT can train on many texts, and based on that, generate new text or answer questions. Same for generating images. Models like Stable Diffusion, for example, can be trained on many images, and based on that, eventually generate a new image based on different queries, I'll call it, or different prompts. But eventually, the idea is the same as any type of machine learning model. So, for example, if I talk about classification models, I have data set of objects and their classes. I can train a model given an object, what eventually is its class. Again, the same idea, the same concept. The difference is the outcome. In this case, the outcome is to generate new data. And what are the differences? Why we are talking so much about Gen AI? What are the differences between Gen AI and regular models? So first of all, complexity. Gen AIs are way more complex than most of the machine learning models. What eventually it means that Gen AI have many, many different parameters to be able to actually answer so complicated questions and be able to hold so much data. And because of that, the cost and the latency of Gen AI models is, of course, different than most of the models. So, for example, to actually run an inference on a Gen AI model, usually I will need a GPU. Usually, because I need to compute so many different parameters, it will require quite a lot of processing. And because of that, the cost of it to make sure we do that in low latency is really high, way higher than simple models, for example. Second one is that Gen AI have, of course, many limitations. So because Gen AI are trained on big data sets, and because Gen AI are actually trained on public data, so first, there is quite a lot of bias in Gen AI because there is bias in the data that we use. And because those models are so big with so many parameters, then it's really hard to understand and find and fix this bias. It's a real problem, and I'm sure that many companies currently are trying to fix this problem and build on top of that. Second is offensive content. So Gen AI, again, trained on public data. It doesn't matter if it's image generation. It doesn't matter if it's generating text. Eventually, it's trained on public data. And in public data sources, we have quite a lot of offensive content. And trying to figure it out, trying to filter these offensive prompts or offensive returns from models is quite complicated. Again, I believe many companies currently are trying to build on top of that because it's such a complex problem, and because it's something that actually hurt businesses that are trying to use Gen AI. And third is privacy. So we all know about many of the commercial Gen AIs. We'll talk about it in a second as well. But eventually, when you use a Gen AI, and I'm sure most of you already tried to use one, you need to send data to it, prompts. It can be internal company data, and receive back returns. You can connect these Gen AI models to your different data sources. And eventually, there is quite a lot of data that goes to the models. You get back from the models, and companies actually need to understand how they manage their data and make sure that their customers' private data, private information actually is secured. So this is another limitation. But of course, on top of that, there are many, many advantages of Gen AI. For example, we're talking about, for example, general purpose models. So models like OpenAI GPT models or models like Google BERT models. Eventually, these general purpose models are really good for many cases, right? We all seen it. We all seen how we can ask questions these models, how we can add different contexts and see how the answers change based on the context. We all seen that for general purpose problems, these models actually give us a great solution. So understand why we need Gen AI models, we understand why generative models actually have benefits over regular models. So because they're already trained, because they're trained on so much data and so much general purpose data, but still there are some disadvantages for these types of models and some things that you need to concern when you talk and want to use Gen AI models. So next is what's the difference between closed source and open source models. So we all know the closed source, the commercial AI models, right? Models, for example, like GPT-4 and DALL-E 2 by OpenAI, models like Lambda that used by BERT by Google, and Midjourney, for example, for computer vision. But there are many open source models in this era. And actually, the open source models keep being more and more actually better. And there are more and more companies that makes these open source models better. So for example, you can see here Bloom and Alpaca and Llama. By the way, Llama 2 was just launched by Facebook, by Meta this week. and Stable Diffusion again for computer vision. And there are many, many examples for open source models. So one of the questions is what is the difference between the two? Why should one choose a closed source commercial model, and in which cases you choose an open source model? And eventually there are advantages and disadvantages to both. So first of all, closed source model, I think that the biggest advantage is that there are great general purpose models. So for general purpose use cases, for cases where you want to have a solution that is actually aware of general purpose data and answer based on that, then that's an amazing solution. And companies can use that, companies can integrate with that. For example, for any type of chatbots, of course, it makes sense. If the model don't need to understand the company internal data, internal knowledge, then you can use that. But there are limited customizations for those kind of models. It's an API model only in most cases, so they stay sent to a third party. And there is high latency, there are rate limitations, and of course, there is cost to those kind of models. And in terms of open source models, so first of all, when you use the open source models, you can use a pre-trained one on general purpose data, but these models can be fine-tuned and can be trained on your specific, your product, your vertical data. And actually, you can use these data to make sure they are more and more accurate. In addition to that, you deploy them on your infrastructure. So you can manage the cost, you can manage the performance of these models, you can manage the rate limiting, and you can make sure that it's actually part of your product and give more impact to your product. What we're seeing as QWAK is that, again, for many use cases, general purpose, closed commercial Gen AI models make sense. We are working with many customers that use actually OpenAI or use BERT or use any type of other open closed source commercial model for the use case where the use case is general purpose, where the use case doesn't involve any private data, and where the limitation of customization of those kind of models makes sense for them. But the problem is once you scale, the problem is once you have more and more data, the problem is once your latency and your cost actually doesn't make sense for your product, and you want to access private information from these models. And for me, we're moving to the MLOps part of it, or how can companies create their own Gen AI model, how they can streamline these process, how they can create a pipeline that actually makes their model more accurate, makes the model private, and make sure that the models actually answer their specific customers' challenges. So I must start by saying that MLOps topic and MLOps for Gen AI doesn't really change between like Gen AI and any type of other regular model. There are some differences and some points where you need to have a solution for Gen AI, where you need other type of resources or other type of data pipelines, but overall it's quite similar. So whenever you build a Gen AI model and you want to serve it in your infrastructure, or you want to, even if it's not on your infrastructure, even if it's in a SaaS provider, like one of QWAK's offering, eventually when you want to serve this model, you need a way to have to serve the model. You need a registry for all your model versions. You need a way to fine-tune your models. You need a way to deploy models and understand which model works better. Run A/B testing, gradually deploy a new version. And it's part of a whole topic in MLOps of model serving, or how you do make sure that your model is served in the right way. And this is a topic by itself. So whenever you create a model, and I'll talk about the model training and automation in a second, you need to make sure that this model actually meet your business needs. You need to make sure that the model can actually run the inference in the latency that you need. And you need to make sure that you understand how to scale this model to respond to your load. And all of this is part of the model serving. So your model serving solution have to have the ability to integrate to your registry, to have this lineage between trained model to deployed model. It has to have the ability to gradually replace models, run A/B tests, and again, make sure that your models can be fine-tuned and can meet your specific needs. The second part of the model serving is the data pipelines. So one difference between generative models and let's call it regular models is the data that is used to build and run inference for these models. For example, as we said before, to train a Gen AI model, you need quite a lot of data. There are many parameters, and to actually have the right value to all of these parameters, you need to run training on quite a lot of data. So you need to create a way to a pipeline basically to streamline your data creation processes. And when I talk about data creation processes, it can be the way that you create the data to actually make sure that you have data for training. So eventually the training data for Gen AI models, that it's a bit different than other type of models, but I won't talk about that too much in this session. But in addition to that, there are actually really good solutions to make sure that models can actually understand your custom data, your highly changeable customer data, and retrieve the right answer, retrieve the right data set from your data sources. And this is creating vector pipelines. So one of the solutions to actually make sure that models are accurate based on your custom data is what we call RAG, retrieval augmented generation. And basically, it's the process of retrieving data from a vector store based on a specific vector, making sure that your prompts and your context are actually are relevant to your specific data. And vector pipelines can help you to do that. So one of the things that we're seeing quite a lot with QWAK, with our customers, is companies creating vector pipelines, saving vectors in our vector store, and making sure that these vectors then be used by generative AI models to optimize the prompts, to optimize the model themselves, to actually use your custom data. And this is an all different pipeline that you need to create for Gen AI models, and is actually can make Gen AI models more accurate and can be used with both commercial models nowadays and private open source models. So this is one part that we're seeing quite a lot. We have a blog post about that. I will share the link to the blog post in the presentation as well. Last is automation. So let's say I fine-tuned the model and deployed it. And let's say I have a solution that creates vectors for my data. Now I need to make sure that I can automate this process. I need to make sure that it's not a single process, it's not a single time process. It's a pipeline that runs whenever I have new data. And whenever my data changes, my vectors basically have change as well, and I have vectors that shows my new data. Same for the trained models. One part of automation is to have the ability to monitor models, and model monitoring it's its all topic. And again, it's quite a complicated topic around Gen AI. There are many ways to monitor models. It can be based on human in the loop and basically feedback. It could be based on specific metrics, but eventually, if you save this data that goes through your models and you monitor this data, you can do many things. From, as I said before, understanding toxicity in your data and understanding bias in your data, and up to the point that you understand if your model is actually accurate or your model actually give your customers the right answer that they're searching for. And based on this monitoring, you can decide what you want to do with your next version. Is it a new fine-tuned trained model, or is it something else? But eventually, based on the ability to track all your data that goes through your model, and based on the ability to actually monitor this data, you can understand how to better serve your data and how to manage your models. So I do want to share what's an MLOps platform, how an MLOps platform looks like. So eventually, let's say I have my data in Snowflake or data in Kafka, it doesn't really matter, but a data in a data source. I can automatically create a features slash vector pipelines that create my data from these data sources, create my features, create my vectors in an automated way. And once I have that, I can make sure that my models actually use this data in real time. So as we said before, the ability for a Gen AI model to actually be enriched by my private data. In addition to that, I can have a build system that builds new version of the models based on my data and deploy them to my production environment. So whenever my model is not accurate, whenever I have a new version, I've changed the code a bit, I can automate my build system and make sure that I deploy the new version to my model serving infrastructure. Once you have the ability to automatically save all your data, save all the prompts, save all the responses. This is for LLMs, for example, but it's the same for generative models for images, for example. Eventually, once I have the ability to save all this data, I can better understand how to automate and streamline this process and how to eventually make sure that this process is actually always accurate. And even if it's not accurate, I can monitor that. I can understand my data. I can understand what my customers ask the models. I can understand if there is bias. I can understand if there is any kind of toxicity. And based on that, deliver my next-gen model. So I talked here quite a lot about fine-tuning models, creating open source models, but it's actually the same process for commercial and closed source models. Because even if I use a commercial model, because it's easy to start with, and again, for general purpose use cases, I think these models are amazing. I still need to have the ability to test between different versions of these models. There are different versions. Each one of the versions give you different responses with different latency and different cost. In addition to that, as I said before, both in open source models and in general purpose commercial closed source models, I have the ability to of some kind of customization. And this customization can be based on my vector pipelines or feature store. It can be based on the private data of my organization. And I can, again, create different versions based on different type of data sources that I have internally. So what we're seeing quite a lot is many companies starting with commercial models and having some experience with that, but they still need an MLOps solution. They still need a single place that they can use to actually streamline this process and make sure that models interact with their vectors or with their features, make sure that they're monitoring these models and creating a build system that can actually build new versions or at least compare between different experiments of the company. So this architecture is actually something that we're seeing quite a lot with our customers. It's something that many of our customers use for their Gen AI models, both commercial models and open source models. And we're seeing how companies can actually iterate faster, create version, experiment faster, and eventually make sure that the models that they deploy in production are as accurate as possible. So we have a few more minutes. I do want to share two more things. So first of all, we do have a few blog posts that were written about Gen AI models and MLOps. So this is 3 of them, but you can go to the QWAK website and find more relevant blog posts as well to enrich your knowledge. Those 3, so first of all, about retrieval augmented generation, and basically an hands-on guide of how companies can use these solution to make sure that their models are more accurate. So this is a really nice blog post that was written by my co-founder and VP engineering and show actual examples of how to do that. Second is how to fine-tune LLMs on your data. So again, I have a model, I have an open source model. I want to fine-tune it on my data. It shows some examples of how to do that, how to make sure that when you do that, you are actually not you're doing it in the most optimized way, and you make sure that you can actually monitor this process and test your models as fast as possible, basically iterate on your model as fast as possible. And third one is some best practices of deploying LLMs in production. So basically best practices to make sure that when you deploy to production, you understand the concept that we just talked about. You understand when you should use the commercial model, when you should do the open source model, what are the differences, and based on that, have a good decision. So again, before finishing this session, I do want to share that there's way more information about Gen AI and specifically LLMs in the QWAK website. You can just go directly to the QWAK website at www.qwak.com, and under the LLM ops, you can actually see more information about some of our customers, how they eventually been able to productionize their Gen AI models, some of their case studies, and even some of the solutions that were specifically for Gen AI and LLMs. And again, links to the blog post. And of course, we're adding more and more information, more and more blog posts about Gen AI and how companies can actually utilize Gen AI as part of their products. So thank you very much for joining this session. You can send us questions through the session Q&A, and we'd love to answer these questions. Thank you very much for joining this session, and enjoy the conference.
Sorry, guys. I had a minor issue here. Thanks for having me here. This is a tutorial about generative adversarial networks 101. Quickly introduction about myself. I've been teaching at Data Science Retreat for a while, and I worked in many different companies and startups. Recently, I've been focusing on being a content creator, so I wrote a book. Then I can give you a link at the end of the workshop. This was all brought to this idea because I wrote a blog post about PyTorch that helped me get going. And at the end of the day, this is one of the reasons I'm give you here this tutorial that uses PyTorch to talk about generative adversarial networks. So I think the first thing that we have to keep in mind is, are GANs still a thing in 2023? They were very popular a couple of years ago, but then in 2022, with the researchers of diffusion models, GANs kind of took a backseat, right? Because they were like, diffusion models were so impressive that pretty much everyone was like, okay, maybe we don't need GANs anymore. This is not quite true, right? Because there have been some developments, like the drag again. We'll give you an example here where you can use some points here to pretty much make modifications and edit the image so they do what you want, right? For instance, like this, making the lion open the mouth, or making the cat close the eye, or these kind of things, which I think that's very interesting, because the whole concept behind GANs is quite interesting. And this is what I'm going to talk about over the course of this tutorial, to give you an idea of how they work under the hood, right? The ideas and mechanics behind this particular kind of model. So without going too much details, right, we're gonna talk about latent spaces, autoencoders. They share some ideas with how GANs work and are organized. We'll talk about generators, discriminators, and if we have enough time, we're also going to talk about a little bit of these other types of GANs that allows you to more easily train models, to have a better outputs. Some examples, I think that this is probably most people are already familiar with, are this person does not exist. That's a website that uses GANs to generate images of faces of people that they do not exist, right? These are not real people. These were just like images that were sampled from a model, and they really look like people. So this was very impressive when they came up a few 2-3 years ago. Maybe this is more common right now, but still, I think that it's important to know this particular class of algorithms, because they bring some advantages when you compare to diffusion models, which are super popular right now. And one of those things is that even though the GAN models are a bit more difficult to train, they are more efficient to run. In the sense that you can generate images more easily and faster than you do with diffusion models. So there is a trade-off as everything, right? Let's talk about the general idea. So GANs is basically, why are they called adversarial networks? Because these are two different networks that are being put to compete with one another. One is called I like to call it the forger, right? So this is the generator. It's going to try to come up with fakes to images that do not exist. And the other one is what I call the appraiser, right? This is the discriminator. This is the other network, the other model that's going to try to tell the difference between if something is fake or if it's not. And to give you an idea of how this works, can go step by step. What I did here, I created a small data set, right? I'm going to skip the details here in the interest of saving time, which is a small named-list-like data set that contains circles, and just circles, right? So we have circles of different diameters. So you have some large circles, some really tiny circles, some medium-sized circles. And the idea is that This should be a problem that's simple enough that a small model, a small GAN model, is able to replicate this circle, right? To generate them automatically without having to draw them as I did here to generate the data set. And the whole thing starts actually with something that's called a latent space. And what is a latent space? The latent space is pretty much a set of numbers that you're going to draw usually from a random normal distribution, or sometimes a random uniform distribution. And they are random numbers in nature, right? So they don't have any specific meaning attached to them. And the idea that the model is going to be used to transform from this random space into something that's meaningful to us. In that case, we want to generate would be images of circles. And then it starts like literally just getting some random numbers. For instance, we can get, in this case, as if we're generating 5 images, right? We have a kind of mini batch size of 5, and each one of those has only a single number. This is a really difficult task, if you think, right? How you go from one single number to a full image. So basically, you need to map from one single value to generate a bunch of pixels. We're going to actually relax this a little bit and make more a larger latent space with like 20 numbers. But still, this is the basic building block which the model is going to work with. And what do we want to do? We want to generate an image out of a set of numbers. How can we do that? Well, what we do is we pretty much use a neural network, right? But that's a quite specific kind of neural network that's called a decoder. What the decoder is doing is taking either it's 1 or 20 or a different number of numbers that are in what's called the latent space, this random vector, and through a network that uses techniques like convolutional neural networks transpose convolutional layers, it's able to reconstruct an image out of this. It does not necessarily need to be a transposed convolutional neural network. We're going to see one of those a little bit later, but it may work even if you're just using like a linear layers like this, right? You may have like a sequence of linear layers like this, and as long as you have the input that matches what you have for latent space, your random numbers that you're beginning with, and in the end you have the proper number of pixels that you want to generate, it should work. So you may have a decoder like this, and you see it starts with just one feature, and in the end it generates 784 pixels like an MNIST image. If we actually run this, right, if you submit a value to the decoder and we see what comes out, this is going to be noise, right? Because the decoder is not trained. It's just, making a lot of multiplications inside the model and generating a random image as an output. And our job is actually, okay, how can we tell the decoder to do a proper mapping between what's the random number that's beginning with and an image that we're interested in. In our case, an image of a circle. So that's what we're trying to accomplish here. One way of doing that, and that's why we talked about autoencoders at the very beginning, is that autoencoders are kind of the other side of the same coin, the flip side of the coin when it comes to this problem. We need to generate an image out of a sequence of numbers, and what the encoder is doing is exactly the opposite. It's taking an image as an input, and it's converting into a really compressed representation of that image. So we get an image of pixels here, and in the end, what you get is just a sequence of numbers, which is the latent space that we just talked about. And what the decoder will do is to go from this back to the other. So if you put the two of them together, you'll have how an encoder actually works. You go to an image, it goes into a representation, and then you get a decoder to reconstruct the original image. So that's when they differ, right? The autoencoder is a model that's built to reconstruct a given input. So X and X tilde here, they should match. They should be as close as possible. And in the middle, it's generating a compressed representation. What we want to do is actually shift this perspective, because we're not encoding an image. We really want to create images out of thin air, out of this Z vector here in the middle, without having to go to the encoder part. And this is what we do with a generative adversarial network. And we see how these pieces of the model are going to be positioned in a different way to accomplish that. So as I said, we start with the Z vector, right? That's the latent space. It's literally just drawing a bunch of random numbers, either from a uniform or a normal distribution. And in this case here, we're using 20, so that we can actually generate decent images of circles. If you try with 1, it's probably going to be a really poor image. It's not necessarily going to work. So we're going to giving it some slack, cutting it some slack, and giving it 20 dimensions to work with. So we're going to go from 20 numbers to 784 pixels in the end. So for instance, I can simply generate a vector here, or a tensor in this case, with 20 numbers, right? This one. And if I try to generate images out of this, guess what we're going to get? I mean, noise, right? Because it's still random. And you can see actually now we're calling this part of the network, this part of the model, we're calling it a generator now. It's the same thing as the decoder, right? What it's doing is getting a latent space, this vector space here, and is applying a neural network to it, and in the end it reconstructs an image. So now I'm calling this X fake, right? Because this is an image that does not exist. There are some tips and tricks that are covered here in the paper, right? So I can provide some links here. I'm not going to go over this because this is a really short session, and I wanted to cover some of the more interesting parts. So this is here if you for reference, right? Some ideas on how the GANs evolved over time and which kind of changes were made to the networks, to the models to make them work, right? So let's skip this and go straight to an example, right? For instance, here we have a latent space of size 20. The number of channels we are generating grayscale images, so that's just only one. The number of filters is 32. And here we're basically expanding these 20 numbers into as if they were 20 pixels, if you will. Like this is kind of an analogy, not quite a pixel, but it works like that. And then we are using a sequence of convolutional transposed layers that they pretty much increase the dimensionality of the image. So you start with a single pixel, and then you have like 4x4, and then you have 16 by 16 pixels. So they allow these layers allow the model to get increasingly larger images, and that is very convenient for us since we are actually trying to go from a compressed representation back into a full-size image. So this is how a generator looks like, and as expected, as I mentioned, right? If we give it an input, a sequence of numbers, it's still going to generate something that's utterly noise because we haven't trained it yet, right? Actually, just before we go to the discriminator part, if you want to have a better idea of what I just mentioned about transforming a sequence of numbers, like a latent space of 20 numbers like this, into as if there were 20 pixels, right? And air quotes for this. Then you would have like this. Each one of the numbers would be like the single pixel in one of those 20 channels. So it really expanded the image. And as I mentioned, what the transposed convolution is doing is actually increasing the dimensions of the images. So here is the formula if you're interested. I wrote a blog post about this. You can check transposed convolutions too if you want to learn more about it. For now, I just ask you to assume that this is used to increase dimensionality, and let's see what happens. how the model is able to tell them apart. What's something that's noise? I mean, because we can clearly tell this is noise, right? If you look at it, but the model needs to be able to do that. And to do what the classifier or the discriminator is doing on the other end of the model is trying to tell the difference. Is this a real image or is this a fake image? And then it's gonna, at the end of the day, you're gonna have a last layer in the end, which works as a logistic regression, right? It's gonna get a bunch of features from the model, and then in the end you have a sigmoid function. You're going to tell a probability if something is real or if something is fake. So here again, I wrote this class that just takes care of the handling the input and output size of a model, and the model itself is going to be something that's kind of the mirror image of the generator. And you see here we also have convolutional neural networks, and it works in the opposite direction, right? If you look at the image here, you see this actually going from very wide to very narrow, because it's getting an image as an input and is really getting it compressing into a much smaller representation in the end. That's going to be used as a feature to tell fakes from real images apart. If you have something like this, you basically want to have this symmetry. So here maybe it's easier to see as printed like this. You see that you have convolutional layers here, 4, and the generator you have again 4 convolutional layers. So it's important that you keep this symmetry in a way that both models have more or less the same the level of complexity. Or in other words, they have more or less the same power. Because if you have a generator that's much larger than the discriminator, it will take over, right? Because these networks are adversarial, and we don't want one of them to easily score over the other. We really want them to keep them in check. So the generator should be good enough to generate something, but the discriminator should be good enough to be able to tell them apart at least sometimes. We want to put them in check, right? We don't want one of them to get too good and the other to trail behind, because then you're not gonna have a decent model in the end. So that's why these models may be a bit harder to train, because they rely on this really subtle balance between the two competing parts. And if you put the model as a whole, right, we have something like this. And you see this is actually flipped from the encoder, right? If you compare to the autoencoder, we had this guy here that would give me a compressed representation that could be used to generate reconstruction here. And in the adversarial networks, actually it's the other way around. I'm using the decoder part, the generator now, to generate something, and then I compare to data that I have for real, and I train this other part to instead of generating Z, it's a simple classifier that tells me if something is likely fake or not. So that's general architecture, right? I mean, you can put them the two of them together, but that's not usually the case, because we're going to train them in an alternate fashion. The training part is something that we're going to discuss. It's a bit different than what's typical for training deep learning models in general. That's why I call it, that's the secret sauce behind these models, are actually the way that you train them. And as I said, you don't train the whole model at once, you take turns. So once for the discriminator, and then for the generator, and so on and so forth. Let's take a quick look at over all the steps. Basically, we're going to start with the discriminator. And what we're going to do with that is we're going to take a mini batch of real images, in this case, the circles that we generated at the beginning of this. And then we know that they are real, right? These are the real images that when we generated them in a different way. They are synthetic, because I chose to get a synthetic data set, because it's easier to explain. If you know how it was built, it's better for studying it. But basically, if you have real images, you know the labels, right? So basically, you're going to compute binary cross entropy loss, just like any other classification task. used in training the discriminator once using the real data. So if we do that, this is like standard classification, right? You have a mini batch of real data here, and then I know the labels are one because I created these images, and then I throw them to the discriminator. The discriminator is going to give me some logits at the end, right? I should, since we have a sigmoid, it's going to give me probabilities, and then I can compute binary cross entropy, so I get a loss. So I have a loss for the real images, which I'm calling conveniently the loss for the real images. Then you may think, okay, but now I need to also teach my model how to handle the fake images. But I don't have a mini batch of fake images, right? I have a mini batch of real images. But turns out, of course, we don't need one. We have the next best thing that's available to us. We have a generator. We can simply ask it to generate as many, an infinite amount of fake images if we want, right? So then let's make a good use out of it. In this case, what we're going to do, we're going to generate a bunch of fake images. They're going to be really, really bad when we begin. We saw those, right? They're just like noise. And we know that they are fake. Therefore, we know that the proper label that they have, they are fake. So the label is 0. But one thing that you need to keep in mind here, we're using the generator at this particular point just to give us back it's an easy way to generate fake images. We're still focusing on training the discriminator at this point. So we use the generator just to literally produce a mini batch of data. So if you're used to PyTorch, you can think of it as if it were a different data loader. And then what you're going to do, we're going to get these fake images, submit it to the discriminator, compare to the labels that we know that they are 0 because they are fake, and again compute binary cross entropy loss. So this is exactly the same as before, but now we have zeros because these are labels for fake images, and we get probabilities. We compute binary cross entropy loss. We get another loss value here, which is called the loss for the fake images. So we have one for real, one for fake. What do we do now? Now we have to actually update the parameters of the discriminator. We have to actually make it learn. And then here, if you check tutorials and materials in general, you see there are 2 different approaches. One is to make 2 updates. So you use the one loss for the real image to make an update, and then you use the loss for the fake image to make a second update. Or you just add 2 of them together, and then you make a single update. There is no right or wrong here, right? I've seen many tutorials and many pieces of code using either. So, at the end of the day, it's a choice that you have to make. But I wanted to highlight this, especially because if you're following someone else's piece of code, you're not aware which one of the approaches they're using, you may actually end up mixing the 2 approaches, right? So it's important to know that if you're using 2 updates, you need to zero the gradients here after making the update. And if you're doing it all at once, you can leave it to the end. So I really think that's important to keep this table in mind to compare the difference between the 2. So when you're doing it the proper way, right? Without mixing and at the end of the day, hurting the performance or making training harder just because it's not following the proper steps. What you can do at some point is, once you know that you have this way of training the discriminator, you can actually put the discriminator to the test. You can see if it's actually able to tell the real images from the fake images apart. Because as I said, if it cannot tell them apart, your model is not going to learn anything. So what you can for instance, start testing it by first, with an untrained model, you can see that they cannot tell them apart, right? If the model is untrained, it's going to do a really bad job. So it is really easily confused what's real and what's fake. But if we train it only the discriminator using this procedure that we outlined here in the above image, and here I'm not going over the details of the loop, right? Because this is supposed to mimic the image that I just showed you. At the end, I mean, the discriminator can easily tell the fakes from the reals. So we know, okay, our discriminator is good enough. So then we can use it, right? It's up to the task. We still don't know if it's like strong enough or too strong to compete with the generator, but this is what we're going to learn. But we know that this is able to do something on its own if given the chance. Oh, we have a good start. Then how do we actually train the generator? And this is a little bit trickier because what in this case, we're going to have to use the discriminator, but we're not updating it, right? So what does this mean? We're once again using the generator to generate some data, but this is the twist. We know that the data is fake, right? But we want to confuse in a way the discriminator. So we tell the discriminator that these fake images are actually real. So we pretend they are real, and we use as if they were real to compute a loss. So I think they may be really confusing if you're beginning to understand the mechanics of this. That's why I called it the pretend data, right? Because you know that's fake, but you pretend that's real for the sake of computing the loss. And the interesting part here is that you're actually going to have to make compute gradients for the whole thing, right? Because the loss is here in the back. We're going to back propagate until here, but we're only interested in actually updating these parameters here, right, for the generator. But we still need the discriminator in the mix, so we can actually back propagate the whole thing until the beginning, which is the tricky part. So for the generator, what do we do? You generate fake data. You use the discriminator, right? We make the pretend labels here. We actually compute the loss using the predictions of the discriminator, and then we backward propagate everything. And you'll see that actually, how can we make this distinction between the two is because we have separate optimizers for each one of those. So one optimizer is only going to take care of the parameters of the generator, and the other one is only taking care of the parameters of the discriminator. Then we can easily make the two hardly separated, right? Because that's important. We want to train them in an alternate fashion. And I know that's a lot of information to take in, right? That's why I made this notebook with a lot of detail. If you want, you can follow it later. But I really wanted to give you a general overview of the whole thing. So you see, we have two different optimizers. And one thing that's also interesting to note is they are different optimizers, which is maybe counterintuitive, but on the other hand, think that you may need to give the generator a head start. So that's how I think that's a good way of remembering this. Because the Adam optimizers, usually it's allow the models to train a bit faster than the typical SGD, right? So if we train the generator using Adam and the discriminator using SGD, we're kind of allowing the generator to train a bit faster, at least in the beginning. And this is important because, as we saw, the first few images that are generated are really, really bad, right? They're just noise. So if you have only noise, the discriminator is going to have too much of an easy life saying, yeah, this is fake, right? Because that's like too easy. If we allow the generator to get a head start, it's going to get some circle-like images to begin with that may be a bit harder for the discriminator to tell them apart. So I think that's a good way of reasoning about this choice. And you see this is fairly common. And if you put the whole thing together, right, the idea is you're going to have like the discriminator here, the real data. So I really made this code in a way that separated in chunks, so you know which part, it is referring to real data, fake data. Then you have the generator, you have pretend data. So you have all the steps in here, right? And also it has some additional code here to generate some samples, so you know how this thing was actually progressing over time. And I ran these before the session, right? Because we don't have time to run the whole thing. So if you run these, you're gonna see these losses. And then in the first thing that when you look at these losses, like, okay, whoa, what is that, right? This is really bad. How can a generator have an increasing loss? And this is also something that I really wanted to address in this short tutorial, because this is super counterintuitive. We are so used to training like regular models and seeing the loss going down, the loss going down, like you're happy the loss is going down. And then you look at this model, you see, okay, whoa, this is really bad model, right? How can I have a generator loss going up? And this is not actually true. This is not super bad, because don't forget the two models are competing with one another. Just because the generator loss is getting higher does not mean that the images are necessarily getting worse because of this competition. So it's not the problem with using this binary cross entropy when you're training a regular GAN is that the losses, they cannot be compared over epochs. So this plot is actually misleading. If we take a look at how it progressed over time, you see that in the first epoch it's really bad, right? Then you get a little less bad. You have some hints of circles at the 50th epoch, some kind of circles on the 100th, and then you have circles when you finish 200 epochs, which is quite decent, right? Such a simple model, and like training 200 epochs, and you still got this. So you see that the loss was going up, but the model was not that bad. Which is, again, I think this is counterintuitive. I really want you to be aware of this, so you don't get scared by the plotting your losses and seeing this kind of picture in. If I generate a bunch of those and compare to some random image that I get from a original data set, you see that in general is doing okay, right? You get some kind of overlap of a small circle and a big circle, some half circles around, but you have plenty of circles that can be, you can say, yeah, this is a circle. Maybe a bit, the definition may not be so great, but still quite a simple model. You're using 20 numbers only to start the latent space, and I think this is pretty decent. And in the end, if we use the discriminator to tell them apart, you see that it is still able to make a distinction. So if we submit those and those to the discriminator, you can easily say, yeah, this is fake, this is real, right? So this is not particularly like the top-notch model that we want, because we really want our discriminator to be kind of confused. Because if it can easily tell apart what's fake and what's not, it means that the fakes are not that good, right? I mean, if you ask like an expert in painting, yeah, this is a Leonardo da Vinci, and the guy said, yeah, duh, it's not, right? Then, I mean, this is a bad forgery. And in this sense is where you want our images of circles to look great, to look like they are really from the same origin as are the ones that we have drawn ourselves at the beginning. We really wanted to see something more in the middle here, right? So these are some challenges, right? So we have uninformative loss because you cannot compare across epochs. The loss still goes a bunch of ups and downs. There is something that I didn't mention, but there is something called mode collapse, which basically the generator finds the cheat code, right? Maybe some combination of pixels that are not meaningful to the human eye, but that they can consistently fool the discriminator. So the generator thinks, yeah, cool, I did a good job. My images are awesome. If we look at them, we say, no, this is really bad, but it's still able to fool the discriminator. So this is called mode collapse. It's a relatively common problem when you're dealing with GANs. I know that we are running short on time, and that's why I call this like a bonus section here. You can address most of these problems using a different loss function instead of binary cross entropy. So this particular loss function is called Wasserstein loss. And instead of being, and you need to make some small changes to the model to account for that. And the most important thing that you need to change is getting rid of the sigmoid function at the end of the discriminator. So it's not probabilities anymore. You can think of it as a score, the logits. But then the labels should change. Instead of using 0 for fakes, you need to use -1 for fakes, right? For the fake images. Then I will not have time to go over these details, right? But a point I would like to highlight here that if the model is doing well, the loss will be negative. So again, Wasserstein loss is kind of counterintuitive because we like the loss to go lower, and then we have one that's actually going up, and now we have one that's going to negative territory, which is like at first sight is really a bit puzzling. But if you think that, okay, given the formula of the loss, it makes sense, right? If the predictions and the labels agree, they're going to be negative. This is because of the way the loss is constructed, right? Should not look too much into that. But you know that if you have a good model, you're going to have negative losses. So let me just quickly go through an example of this. There is also something called the gradient penalty. You need to make it easier for the model to converge to a solution. I'm sorry, I'm not going to have the time to go through details here, but you can look at the notebook if you want. And then one small detail still that needs to be taken into account is that in this case here, the discriminator, or it's called the critic, when you change the loss, it actually is going to be updated several times over before we give the generator a chance, which it kind of goes against what we said about making them on level, right? But this is something that was proven to work better for the convergence. So this is something that you can do. And then you see here losses are really negative. You can see generator loss is going to negative territory, and then it's much more stable now, right? The discriminator loss, it's also negative, even though it's a different level. So I mean, we should have a good model like this. If we can check the evolution as we did with the regular one, you see that it actually gets a bit better. I only ran it for 50 epochs here because it takes a little bit more time. Because the model is with a different loss, it takes a little bit longer to train. But even if it's still on 50 epochs, if you compare to what we had at the same number of epochs before, this is better, right? If we go for 200, probably going to have much better circles. But nonetheless, if you compare the generated images against the real images, it's still pretty decent, right? And now if you compare how the critic is making the distinction between the two, the real and the fake, and notice that these are not probabilities anymore, these are just scores. You see that there is a huge overlap between real and fake. It's because this particular discriminator critic cannot tell so well apart these two. I mean, we can, right? We can clearly see that this is fake, but the model still cannot. So maybe if we train it further, we get much better generated images still. And yet, this pretty much wraps up. We have 5 minutes left, I think. I wanted to give you a general overview of GANs in general, right? And how they work, how these minor pitfalls and things that may trip you over if you're starting learning them. These losses, negative losses, these kind of things, I think they have some peculiarities that are particularly counterintuitive when you compare to regular deep learning models or models in general. So that was my idea here. This code is available at the GitHub that I posted on the channel there, so you can go over in more detail. And yeah, I hope this helped you. I'm available here on LinkedIn and Twitter. I wrote a bunch of books, so if you like PyTorch, if you want to learn more about PyTorch, give them a shot, give it a look. Thank you so much for this. Let me see if we have any questions. So I see Do you have insights on the abilities to use GANs to generate synthetic tabular data? The use case I have in mind is taking a small data set of customers and using GANs to generate additional data that can train ML models. So yes, actually there is a use case for this. I know that GANs are successfully used to generate tabular data, which is I would say quite impressive. I remember the one particular package called the Y data, if I recall correctly. I can look at in more detail and post it on the chat after we finish here. And then what they do with this package is exactly that. They try to generate synthetic data that can take a tabular data and try to replicate it in the way that it possesses the same underlying structure, right? But then you can probably work overcome problems with anonymization, this kind of thing, right? Which I imagine this is one of the reasons to try that. Yeah, I don't know if you have any questions. Let me check. No, I think that's the one. Yeah, I mean, thanks a lot. I hope you enjoy this. If you have more questions, you can type it in the chat. I'll be happy to try to reply to the best of my knowledge. And I think I missed a link out too about the transpose convolution, because this is a topic that can be interesting to you too. If you want to know more about this, I can post these on the chat as well. Yeah, I mean, thanks a lot, and yeah, you're welcome. And I hope you enjoyed it.
Hello, everybody, and welcome to the Generative AI Summit, Stage 2. We are here today with Emily Weber, Principal ML Solutions Architect at AWS. Emily is a machine learning specialist solutions architect, and she's been leading data science projects for many years, piloting the application of machine learning into such diverse areas as social media violence detection, computer vision, reinforcement learning, the Internet of Things, drones, and robotic design. And as a quick reminder, this week is our last week for 70% off of ODSC West. So if you're interested in coming to the event, either in San Francisco in person or virtually, be sure to get that deal by tomorrow. And now, with that, over to you, Emily.
All right. Hello, ODSC folks. Thank you for joining me. Thank you, Alex, for the introduction. So today we are going to learn how to pre-train vision and language models on AWS. So with that, let me get my slides shared in the screen here, and then we'll take it away. All right, beautiful. So here we go. So again, this is a tutorial. So the purpose of the session today is really to give you fundamental knowledge. Like I want you to walk away knowing how to pre-train your own vision and large language models of the future, because who doesn't want to do that? That's the coolest thing. So let's check it out. All right, so let's assume that you want to build your own foundation model. Llama 2 maybe isn't good enough for you for whatever reason, and so you're interested in creating your own. So in the session today, first we're going to understand why you would want to create your own foundation model, also known as pre-training. We're going to look at when you would want to do this in your project lifecycle. We'll understand a few base models to pick, what data sets you might want to use, and then how you can do this easily and efficiently, particularly on AWS and on SageMaker. We'll close things out with a hands-on demo. So this is a demo about pre-training a 30 billion parameter LLM on AWS using SageMaker distributed training. All of the resources are available for you. So if you stick with me through to the end, you'll get a link to the slides, and all of the content that we're going to cover today is related to my book, actually. So I've written a book about pre-training vision and large language models. And so you can dive deeper into those topics as you like. All right. So let's say, just for the sake of argument, let's say I asked you to learn everything on the internet. How would you go about doing it? Now, obviously, you're going to say, well, hey, Emily, that's impossible. I'm not even going to try. You would be right, but let's pretend that that's not the case. Let's pretend maybe in some universe it's possible. So you'd build some type of structure for just holding all of the files or even holding all of your notes. You'd map out some type of decision tree that's going to tell you, hey, first I need Wikipedia, then I need Reddit, then I need all of these other data sources and news feeds and all sorts of things. But your single largest obstacle is going to be your time. It's going to be the human time that it takes to simply read and to learn and to grapple with the concepts and try to relate all of the concepts. That's the largest obstacle. So last time I checked, there are almost 6 billion pages on the internet. Now, obviously, that's growing every single minute. So that number is no doubt stale as of yesterday. But so in any case, let's say you've got 5.75 billion pages on the internet. And then let's say that the average person actually spends 52 seconds looking at a single page online, which is a little depressing. We know that it's many more than 52 seconds to create content, but let's assume that it's about 52 seconds to read the content. So that takes us to nearly 85 million hours just to read everything that's on the internet today. And then if you translate that into human years, assuming that humans eat, we sleep, we like to take weekends off, we like holidays, we only work a certain number of hours in a day. So that's going to take you right around 41,000 human years just to read everything that's online. A foundation model is going to do this in a couple months. So that's the real reason why LLMs and why any type of foundation model is so exciting. It's because they're extremely powerful. They hold massive data sets. They have the capacity to learn the representations of the content in those data sets. And so they're these extremely powerful beasts. And so we want to learn how to use them. Obviously, foundation models can do a lot because when they're performing this unsupervised pre-training, they're capturing many different types of tasks. So they're capturing not just classification, but they're also capturing summarization and question answering and rephrasing and arguably search. Obviously, they're capturing code generation and image and audio and video. And so there are many different ways that foundation models can solve many different tasks. And so that's why we're drawn to foundation models. As we're coming to find out, many ML tasks can now be recast as quote unquote generative or can leverage this foundation model in some capacity. So historically, you might take a text like this, saying I'm not into this house, it's too expensive, too far from the train line. And you'd build a classifier, right? You'd build this small model to perform binary classification on this that's just sorting it into positive and negative. That's your traditional classification. Now in the foundation model world, we're going to take that text, but we're going to add an instruction. So we'll add an instruction into the prompt itself. We'll send this to the model, and we'll ask the model to then classify that sentence into positive or negative. And so the agent can then respond. And so there are many ways that traditional machine learning tasks are being reevaluated and re-explored to use these foundation models given their potential upsides. There are many ways to customize a foundation model. So let's assume that you've picked a foundation model, be that a vision model, be that a language model, be that something that's larger, something that's smaller. There's a large spectrum in different methods that you can use to customize that foundation model and better suit it for your purposes. Now, I would argue that there are two axes that you want to pay attention to. So one, obviously, down here on the x-axis is complexity and cost, which is to say some of these techniques are easier. They're not as hard, they're faster, they require less education, they're just straight up more simple. And as a corollary, they're less expensive. Now on the flip side, on the y-axis here, though, you see this accuracy. And so accuracy plus, bear with me. I mean, the quality of the model performance, obviously, we're not laser focused on that specific KPI. There are quite a few, but nonetheless, you see this relationship. And so prompt engineering, of course, is a way to interact with a foundation model, to customize the performance of that foundation model. Retrieval augmented generation, or just more simply search, is a way to, of course, find a document that's answering a question more directly that your user is asking, and then essentially have the LLM select the answer from that document and then provide that to the user. Fine-tuning, and again, there are many ways of doing fine-tuning, is another technique, obviously, to bring your own data, use the model as a base, and then fine-tune this model to better understand your data sets, better understand your domain that you're interested in. And then pre-training is sort of this holy grail, right? So pre-training is the most complex and, of course, the most expensive thing you can do to solve a problem. But it also tends to be the most accurate way to end up solving your problem in full robustness. And so this is the primary reason why you might consider pre-training your own foundation model, is because you want to see that accuracy upside. But we're going to figure out how to get there. So one reason why we're here today is Richard Sutton, who you might be familiar. He's sometimes called the father of reinforcement learning. So he's this classic figure in AI research. Back in 2019, Richard Sutton sort of famously threw up his hands in what's called the bitter lesson. And so he tells us that the biggest lesson that can be read from 70 years of AI research is that general methods that leverage computation are ultimately the most effective, and by a large margin. He tells us the only thing that matters in the long run is the leveraging of computation. So what this is saying is that after 70 years of hard work in AI research, what Sutton is telling us is that the best techniques are the ones that are the most scalable, that use the most compute in the most general way, because he says that in the long run, that's actually the most effective. So I would argue that this is a anecdote that's underpinning why pre-training is so valuable and why it's such an interesting project to go after. So I believe that pre-training might actually be the best long-term bet in AI. I have yet to see a case where pre-training doesn't actually improve performance. I would love for someone to tell me cases where they've seen this. I'm quite curious to hear about a negative. But so far, pre-training appears to be the best long-term bet. Now let's understand why. So when you are pre-training a new foundation model, the loss function itself is different than when you are fine-tuning or when you are customizing a foundation model. What does this mean? This means that when you're pre-training your foundation model, the mathematics are actually better suited for general learning, which is to say your model is learning general trends from your data set without needing to be explicitly taught this. So think about like classes that you've taken and some of the classes that you've taken throughout your career, throughout your lifetime. I would argue that possibly some of your favorite classes were maybe the most open-ended, where you were asked to think, you were asked to stretch your mind, you were asked to evaluate, many different options. And it wasn't just someone telling you like, oh, this, remember. It was someone pushing you to dive deeper and to explore the core trends. So I would argue that pre-training actually seems to have just a straight up better loss function. It just learns at a deeper level than some of the other techniques because they are just higher. They're higher up in the stack, they're higher up in the model weights, and they are learning more discriminative sort of basic mapping. Like when you fine tune a model, generally you're learning a mapping from O string A to string B, whereas in pre-training, your loss function is just at a lower level. So it appears to be able to just capture these deeper representations. So that's one reason. Another reason is that unsupervised data sets are always larger than labeled data sets. This is because labeling data sets is expensive, it takes time, it takes human beings, it takes software, it's an investment. Whereas unsupervised data are just much more available. All data starts by being unsupervised, arguably, and then only becomes labeled or only becomes supervised after some investment and after some review. So unsupervised data sets, again, are always more available, which means that using the larger data set should logically get us better performance. And then we talked about how the model is actually learning at a deeper level when it's pre-training versus when we're just fine-tuning or when we're just doing prompts engineering or retrieval augmented generation. The potential for the model to capture trends and capture content and knowledge is just deeper when you pre-train than when you operate elsewhere. And then the last reason is that it's just so much more efficient to put all of our resources into, and by our, I mean people in AI ML, people in data science, like when we put all of our focus into one model and make that model amazing and then use that model in a bunch of different use cases, it's just a more efficient use of resources versus when we go after n number of models and we have all of these different tiny models that we then need to fine tune and update and modify. So I believe that those efficiency gains are stronger for pre-training than they are outside of. So that's why I continue to be very interested in pre-training in the long term. Now, if you're going to consider a pre-training project, there are two charts that we're going to want to take a look at. So the first chart is I want you to build a chart that looks at these different model optimization techniques. So looks at your zero-shot prompting, single shot, few shot, parameter efficient fine-tuning, and then classic fine-tuning. And what you're going to see is the accuracy or the performance of your model is going to get better and better with these different techniques. So again, zero-shot prompting is when you just ask your model, you know, hey, what's the weather like in Washington, D.C.? Or what is 1 + 1? You just ask it your question and you expect to get a perfect response. In reality, many times you need to give your model some examples. So single shot prompting is when you bring in one previous example of the type of learning you're looking for. So whether it's translation or summarization, you bring a previous example and you just put it in the prompt. So in the prompt, you have one example. And then few shot prompting is where you bring a number of these examples. And so you have maybe 3, maybe 4 examples of the type of learning that you're looking for, and you put that in the prompt and get a better response. Parameter efficient fine-tuning is a great way to basically freeze most of your weights actually, and then inject these tunable blocks into your model to be hyper efficient, which requires less data and less compute resources because you're fine-tuning a much smaller segment. And then classic fine-tuning, arguably parameter efficient fine-tuning is getting better and better. So it's not always clear if classic fine-tuning is going to be actually better than PEFT, but in any case, and then classic fine-tuning, of course, is where you're actually fine-tuning the entire model. And so what I'm saying is that across all of these techniques that we've looked at, it's very likely that pre-training is going to be much stronger than this. But before I sign off on your project, I want you to go build a chart like this. So I want you to do a little experiment, actually. We're going to do this experiment because pre-training is very expensive. It's extremely computationally heavy. And so before you click go on that job that launches hundreds and maybe even thousands of accelerators, I want you to prove empirically that at a small sample of your data, pre-training is actually worth your time. So let's explore this. So let's say you pick some open source model, and this open source model might be a 50 billion parameter, it might be a 7 billion parameter, and just make sure it's in the same family and trying to solve the same problem as the model that you want to pre-train. Now you're going to take that open source model and you're going to fine tune it, right? So you fine tune it on the downstream task that you care about. And then you compare it with your labeled data and you get some accuracy KPI about how well this model performs. Now on the flip side, I want you to take a new LLM of the same size as this, and you're going to pre-train this thing on 1% of your data. You're going to pre-train it on a very small sample of your proprietary data that lives in your organization. And again, the reason you're doing this is because your data is very different from what's online. It has the robustness of your organization, it has your knowledge, it has all of the juice, it has all of the goodness of what you want to provide to your customers. And so you're going to explore how well that performs in your LLM. So you're going to pre-train a model on your 1% of that data. And then I want you to fine tune that thing. So then after you've pre-trained it, you're going to fine tune that model on the same data set you fine tuned this open source model. And now what I'm telling you is that it is very likely that your pre-trained model is going to be better than this thing. And so once you're able to prove that out, then you can start your pre-training project in earnest, and you have a really strong case for being able to prove why this is so valuable. But that's really your first step. And so what does it take to pre-train a new foundation model? Let's say you really want to do this. So here are 3 foundation models, all of which were trained on SageMaker. And just based on the papers from these models, we can see what it took to train them. So interestingly, vision models, so Stable Diffusion, overwhelmingly tends to be much larger data sets. So the data sets tend to be very, very large in computer vision, but the models are quite small. So this means that for Stable Diffusion 2.1, which is a data set of 5 billion images, 5 billion image text pairs, which then translates to about 240 terabytes of data on disk. So 240 terabytes. But then the model is quite small, right? The model tends to be less than 1 billion parameters, which means it fits on a single accelerator. And so the overall cluster, the total number of instances that you're going to use to train this model is actually lower. The data set is larger to create this new foundation model, but the cluster itself is much smaller. And then as a corollary, the time to train this model is also less. Whereas in language, the data sets you're using tend to be smaller. So in language, both Falcon and Bloomberg GPT, the estimated data set size on disk, in the case of Bloomberg GPT, that's around 2 terabytes. And then for Falcon, that's closer to 3 terabytes. And so for both of those, the model size is much larger, right? The model size is in the tens of billions of parameters. So 40 billion in the case of Falcon, and then 50 billion in the case of Bloomberg GPT. And so as a corollary, the cluster size is much larger. So 48 P4D instances and then 64 P4D instances, and both of them clocking at around 2 months to train the model. Now, one call out here. So Bloomberg GPT, I understand that there's a speaker from Bloomberg on the summit. So I hope you enjoyed his talk. I hope you're learning from the case study. But in any case, what's really important to know is the data set that they used in Bloomberg is an even mix, approximately even mix of open source common crawls. So data sets that are commonly used in training other LLMs, but then half of their own proprietary Bloomberg financial data sets. And this is to ensure that the model understands financial news, not just what is on Wikipedia, but what is actually in the financial news and in financial content. And so when the model is, again, much more intelligent and much more knowledgeable about that specific domain, then this becomes a very valuable asset. So now we've looked at foundation models. We learned about why we would want to pre-train a foundation model. We talked a little bit about the data sets. Let's understand how we're going to do this. So really the first thing once you get to how to do this is just gathering your data. So again, if you're in language, you want to gather a data set that's anywhere in the 1 to 2, possibly 3 terabytes of high quality language data. And as we saw in Falcon, you want to deduplicate that data as much as possible. So you have a really high quality data set that's not overly repetitive. So you're going to gather that data set, park that, for example, in S3. And then obviously you're going to process that data set for training. So that's running tokenization on the NLP language to produce the tokens. What we're going to look at today is using actually SageMaker training, but running CPU jobs in order to do this very cost effectively. So we'll look at data processing techniques, again, using CPUs in order to transform those data sets for training. And once you've transformed the data sets, you're going to optimize your data storage. So FSX for Lustre is a great option to connect into your data sets in S3. Basically, you'll store your data in S3, and then you can create an FSX for Lustre volume, which is a distributed file system that scales linearly with reads and writes, actually. So you'll do one copy from S3 into Lustre, and then as many accelerators and as many jobs and as much iteration as you need to do. You're never going to do that copy again. That is a one-time copy. It's a beautiful thing. And then as you're writing your model checkpoint to that Lustre volume, that will be sent back to S3 dynamically based on the two-way data repository that you can enable. If you'd like more content about that, I'm happy to share some resources. We'll take a look at that in any case. Once you got your data set optimized, then you're going to move into developing and testing training scripts. And again, number one pro tip here, use small instances. Save money on instances as much as you can. Here, you're going to save money by using CPUs. Here, you're going to save money by using smaller GPUs. So literally smaller, older GPUs that are more available. My go-to is still the G4 DN.12 XL. Beautiful machine. I never have problems with availability on that thing. It's a wonderful experience. So yeah, use smaller instances. And then we'll actually look at a way in SageMaker Studio that you can easily switch back and forth. So you can go from a CPU to a GPU. You can do a one-click upgrade to a really large machine, bring that back down to a smaller machine. You can use warm pools on SageMaker training to just develop really, really quickly and iterate. You can track all of it with SageMaker experiments. You can debug it. You can profile it. Lots of things you can do as you're developing and testing that script. Once you have your train script running and you like it and you're happy with it, then you're going to scale up your training run. And so you're going to scale up your training run to the maximum cluster size, data size, and model size that you're interested in. And then let the baby run. That's going to sit there. 2 months later, you will have your own foundation model. And then obviously you're continuously evaluating the model artifacts at each stage to ensure that the performance is where you want it to be. So let's take a closer look at each stage of this journey. So what it looks like in action, I like to set a plan for my project to scale pre-training in stages. So again, I don't want you to just go straight for the largest cluster size. That's not a good experience. What I want you to do is start really, really small, right? So you're going to start at a 1% sample of your data, something really, really tiny, and you'll use the base version of the model. So you can still obviously go for your GPT-2, go for any latest foundation model that you're interested in, and just start at the absolute base version, just the smallest version that one ships at. Use a cluster size with maybe just one accelerator, and then run this just for a couple hours, right? You're going to time box this and just see how well the smallest model can learn reasonable representations and reasonable patterns from that 1% sample of your data. And then do that fine-tuning experiment to make sure that pre-training actually is improving your end results. So that's your first phase. And then your second phase is moving from one accelerator to multiple accelerators. So after that, you might move up to an 8 accelerator instance, and you'd increase your data set sample as well. So you'll add more data to this, and you might increase the model as well. In a multi-accelerator single instance, you're looking at data parallel. So you might be running a data parallel training regime with some minor model parallelism. We get to that in a second, no worries. And then this might take you a couple days, right? That's a couple days of developing. That's some time to train. Might take a couple days to train, depending on how much data you're throwing at it. And so that's to ensure that you can indeed do data parallelism and do model parallelism, and that you're still getting a valid model artifact. Now, after that, you might move out to 2 instances. So then you have actually 2 instances. You're still using 8 accelerators on both of those. So 2 instances. And you might use a much larger sample of your data. You might use a much larger model size. And it might take you a couple weeks to nail everything down, to ensure, again, that your process is working start to finish. And then once you've made it to the 2 instance, then you're ready to go all the way. So then you can scale up your model to the largest size you're interested in, use the maximum pull of your data, and then run this for long periods of time. And again, the linchpin here is checking your model checkpoint. So downloading the model checkpoint, ensuring that it's working, that you like it, that the response is consistent, and that it's still better than what you're able to see in the open source LLM. And so we come to find out that there are many ways of distributing our training jobs, and it's really this core technique, this core skill that you want to learn how to master in distributed training, which will unlock this whole universe to you. So if you want to get serious about doing your own pre-training jobs, what that means is you want to learn how to do distributed training really well. So the first type of distributed training is pretty easy. This one's called job parallelism. And it means we're going to take one set of data and we're going to run a bunch of jobs that are using the same script, but they're going to attack different chunks of that data to process it, modify it, tokenize it. So let's take a look at how to do that. So job parallelism is where you have a list of some processes that you want to run. This could be a list of models that you're trying to train, or it could be a list of chunks in your data set. So maybe you've got Parquet files and you want to pick up each Parquet file and do some processing on that. So you're going to loop through your Parquet files. For each of those, you'll point to the S3 path or the Luster path, and then you'll get the input and the outputs for that. You'll define the estimator in SageMaker that wraps everything you need to run that job. And then you're going to call model.fit. So the same way you train a normal model in SageMaker training, you'll call model.fit. But again, the one parameter here to note is just this weight equal false. So just make sure to turn that thing off. The default setting here in the SageMaker Python SDK, basically while that job is running, the SageMaker Python SDK will think the process is still active. And so in Python, it'll just show as like a variable that's still being executed, which will halt your kernel. So if you're in a Jupyter Notebook running this, then that Jupyter Notebook is just going to hold still. And it also means you can't really do the loop. So if you want to actually do this loop, then you set wait to false, and then all of those jobs are just submitted. So your loop will just submit this job and then immediately go to the next step in the loop and all the way through. And then you'll have all of these jobs that are started basically at the same time. And so again, each of these jobs can point to S3. They're going to store the metadata and all the hyperparameters in the SageMaker control plane. You'll stream all of the logs to CloudWatch so you can troubleshoot and debug and manage all of the processes. And so the first step to processing your data, again, is really using job parallelism with CPUs on SageMaker training. And so once you've done the data processing, then we're going to learn this first type of true distributed training, which is called data parallelism. So let's try to understand data parallelism. So data parallelism is a way to train one model, but use many different accelerators. And you might be using accelerators that are in a single instance. And remember, accelerator means like a GPU, or it means a Trainium chip. It's an optimized processing unit that goes faster for machine learning, basically. And so you want to train a model that can operate on as many accelerators as you can. Data parallel means you're going to be literally making copies of this model. So you'll have one model, but it's copied onto all of the accelerators, and then the data is sharded. So you'll send half of the data set to each of the accelerators, and then we're going to aggregate it. And so there have been many projects to improve this sort of distributed gradient descent or this distributed machine learning training over time. One of the earliest versions was called this parameter server approach, where you have one sort of leader node that's keeping the copy of the model and sort of has all the core data, and then is orchestrating many number of worker nodes. And the worker nodes are all doing the forward and the backward pass, They do the forward pass. They send the results into like the central manager, and then the central manager updates the model and then sends the results back out, and then they all continue. And so parameter servers are actually somewhat bandwidth light, but they're a little bit slow. And so that slowness led to the MPI all reduce algorithm that you see on the right-hand side, which is common in Horovod and PyTorch distributed data parallel, where basically you have all of the nodes that are operating literally like a ring. So they're all talking with each other, they're communicating with each other, and then they're also again passing the updates of the model to all of the nodes. And so at AWS, we've developed custom algorithms to improve distributed training. The paper is available, so it's called Herring, Rethinking the Parameter Server at Scale for the Cloud. You're welcome to check that out. And what's exciting is that this custom approach actually overlaps the backward pass of the model with the communication. So the overall communication is 20 to 40% faster than it would be on AWS, actually. So it's optimized for the AWS network topology. And what this means is that, like, let's say you're running some 8-node distributed training job on AWS, but you're not using this optimized backend. When you plug into this optimized backend, you're going to see a 20 to 40% speed up using this enhanced topology and this enhanced networking backend. And so SMDDP is a great way to run extremely large clusters on AWS. And so now that we've learned about data parallelism, which is having a small model that fits on a single accelerator and making copies of it, let's learn what we have to do when we have a large model. So when the model itself is too large to fit on a single accelerator. And so that's called model parallelism. And then model parallelism can be broken down into two kinds. One kind of model parallelism is when you have different layers. So you have different layers in your neural network, and you're going to place each layer on its own accelerator, or you'll place them on different accelerators rather, and then train the entire model using the sort of pipeline parallelism approach, where you have different layers on the accelerators. That's compared to tensor parallelism, which essentially the layer itself is much larger. The layer, such as a multi-head attention layer, is too large to fit on a single accelerator. And so you need to split that layer itself across multiple accelerators. And so that's tensor parallelism. So SageMaker model parallelism is a library that you can interact with to easily partition and shard your model across multiple accelerators. So we'll handle the model partitioning for you, and we'll actually execute the layers and the tensors at different points in time to maintain stable GPU and accelerator utilization. Obviously, this is synchronized beautifully with SageMaker training and works great with PyTorch. So SageMaker model parallel, we're going to get this exciting little GIF here, this view. So basically, in a model parallel world, we're going to take your mini batch, so the mini batch that you use to train your model, then we're going to split that into micro batches. So let's imagine that in this 4 GPU little cluster we have here, little instance, let's imagine that each accelerator has one layer from the same model. So it's one model, but 4 different layers that are on 4 different GPUs. And so in this case, we're going to split, again, the data. So we'll send different parts of the data to different layers to send them forward through the network. And then once each layer has gone through an accelerator, then we can run the optimizer and then propagate that back through the network. And so essentially SageMaker model parallel is a way to easily run your model across multiple accelerators. So again, imagine it's one model that you're then running on multiple accelerators. And then, of course, what you actually need is a way to combine model parallelism with data parallelism. And so last year, our science team developed a capability that's called MIX. So it minimizes the communication scale. The paper is presented here. It's also public. And this essentially is a novel hierarchical GPU communication strategy or accelerator communication strategy that will first look inside a data parallel group. So first it looks across all of the accelerators for one copy of the model, and then communicates for multiple copies of the model. And so in any case, this is called sharded data parallelism. It's going to be almost 3 times faster than deep speed. It hits a 99.4% linear scaling efficiency from 128 to 512 GPUs. And this is the hands-on demo that we're going to take a look at later in this session. All right, so we've covered how to pre-train your model, but then what about this reinforcement learning with human feedback? Isn't that something we should be tracking as well? Doesn't this help us create the best models in the world? So what's interesting about RLHF, one of the reasons why I love it, is because it is a great way of dealing with a pesky problem in humanity, which is that not all human feedback is the same, right? There are different kinds of human feedback. I would say that one type of human feedback is sort of objective. It's like, yes, all humans agree that indeed 1 + 1 = 2. You can have a literal translation that is actually accurate. You can see some sort of external outcome that literally did or did not happen. There are empirical observations that are undeniable. There's, the difference between black and white, for example. It's very obvious, like all humans agree on this. On the flip side, there's something that's called subjective human feedback, which is where not all humans agree, and reasonable humans have different opinions. This is like interpreting artwork, like reading a book, like watching a movie. If you and I watched a movie together, you might like it and I might not like it. You might relate to one character and I relate to a different character. That's just because people have different personalities, right? Our guts respond to things differently. Things hit us in different ways. And so subjective human feedback is like a massive grayscale, right? Where there are many, many, many different interpretations. So objective human feedback, I would say, is great for a traditional ML task. It's great for a discriminative ML task that's looking for obviously positive and negative, or obviously we're going to forecast this, we're going to recommend that, sort of more traditional ML tasks. Subjective human feedback, on the other hand, is great for generative ML tasks. So when we're generating images, generating language, generating content that can be used in art, in media, in marketing, in all sorts of ways. So you see this sort of subjective human feedback. We want to capture that and use that to train our models. So reward modeling is a great way of aggregating this human feedback at scale. So let's imagine that you've picked some type of foundation model. This could be your foundation model that you've pre-trained, or it could be a foundation model that you're working with over the internet somehow. So you have this base foundation model. You're going to collect prompts. So you'll take your prompt library, you'll send that prompt library to that LLM, and then you'll get multiple responses. So multiple responses from that model or from many different models for each prompt. So this one-to-many prompts data set is really important. Then you're going to use human labelers or just integrate it into your software, depending on how you have it set up, to rank those responses, right? So you'll give them not just one, but many different responses, and then they just pick their favorites. So they rank the responses. You're going to use the result of this human labeling job to actually train a reward model. So the reward model is still an LLM. It's a small LLM. but it's an LLM that takes language, but it's going to output a number. It outputs a scalar, and then you're going to use that reward model to train a new generative model, such as fine-tuning a generative model using reinforcement learning. And then same as last time, you'll evaluate the model and you should be able to see a sizable performance boost. So after you've fine-tuned your model, you should see a big jump. And so this is called reinforcement learning with human feedback. In a nutshell, in reinforcement learning with human feedback, just as we saw, we'll start with a data set of prompts and responses. We'll send those to humans for ranking, and then we'll train a new reward model, and then we'll train a reward model, and we'll use that to update the LLM, which again should be better than the original. So let's do a quick recap of this. So some of the vocabulary that we care about, obviously reinforcement learning is a type of machine learning that's commonly used to train robotic agents, or is used to train video games, is used to train drones, some type of reinforcement learning. And so in reinforcement learning, you have an agent, which is this autonomous entity that we want to train. This agent has a policy, which is how it learns, and that's usually a neural network. And then it's taking actions inside of this action space. And then the reward function is a signal provided to the agent that's driving its learning. So your agent uses its brain, which is a policy, to pick the action, picks an action, takes the action produces a result, and then we send that result to the reward signal to then update the policy. So that's reinforcement learning. Now we're going to apply reinforcement learning to updating the LLMs. And so the policy, again, is the neural network. That's the LLM, and that's going to be orchestrated by some type of optimization regime, whether that's PPO or DPO. And then the action space is, of course, all possible tokens in the vocabulary. The reward model, again, is trained on those human ranked responses. So we're going to move a little bit faster here because we're running short on time. So mathematically speaking, what we're trying to do here is we want this reward model that takes the prompts from the data set, which is X here. So it takes the prompts from the data set combined with the text generated by the LLM using those prompts. And then it also, and that's the one that we're training. That's the sort of active LLM that we're training. And then it also takes the original LLM. So that's sort of Y0. We're going to combine those. So first we take the X and the Y star, put that into the reward model, get this R theta that tells us what humans prefer. Then we're going to put that Y star with the original into this divergence function to prevent the RL hacking. And then we're going to send both of those, so this reward theta and this reward KD, into the PPO. And then we're going to use that to tune the LLM. And so the reason why we care about this, again, is because we should be able to see a 2 to 3x boost over base GPT. Again, you need a large language model. It doesn't have to be massive. 6 billion is good enough. And then again, the data set is going to be a one-to-many. So your prompts can be, what's the weather like in DC? And then you might have different responses, right? So a more sort of dry response tells us that it's sunny and humid. You might have this emotional, it's freaking hot. But then you might say like relative to Phoenix, Arizona, DC is a cool 82 degrees. And so again, the humans rank these based on the instructions you provide them and based on how they're feeling and sort of what they like. And then we're going to use this data set of the prompt and then the ranked responses to then train this supervised reward model. So when you're building and training a reward model on AWS, it's not very different from training a normal model. You're going to use some type of notebook, probably a SageMaker notebook, to analyze your data, develop scripts, and run jobs. You'll store those data sets in your S3 bucket. Again, you're building scripts, which you might store in, the scripts you could store in S3. You could just store the scripts in your repository. You're probably going to be building images such as in ECR. And then you're training the model itself on the SageMaker training instances. And then, again, you're going to use the reward model to train your original LLM. So I would say first you'd have your prompts data set in S3, and then you're going to take that original pre-trained LLM, and you might run a CPU job or possibly even a serverless job to walk through your prompts data set, hit that LLM, store the prompts and responses from that original LLM. And then you're going to use that to train a new LLM. So this might be on a heterogeneous cluster, actually, to use the best of the instances. And so your reward model is going to use a smaller number of accelerators because it's a smaller instance and it's a smaller model. And then that's going to interact with the larger LLM. So the larger LLM that you're fine-tuning is going to get responses from the last epoch in your tunable LLM, send those to the reward model, which is here, run the penalty function, and then use that reward model to update the LLM. And so this is one way to do this. All right.
Hey, Emily. Yep. Sorry to interject, but we are running over time. And we have another session on the agenda starting now.
All right.
So this is clearly a very informative, in-depth session. But if anyone has any questions, there will be a live chat where you can drop this link or anything interactive on at live.summit.ai under your channel. This way people can continue along as they need. And if you have any wrap-up comments, then please go ahead.
Okay, yeah, thank you so much. So just a few QR codes for you. So the slides are here. Feel free to grab this and download the slides. And then really, if you want to dive more into this, go ahead and check out my book. My book is available on Amazon. That's the QR code and the short URL. This dives into all of these topics and more. So the book is really to help you learn how to pre-train your own models and your own foundation models, especially in Python, on AWS using SageMaker and more. So with that, thank you so much.
Thank you very much, Emily. Okay, up next, we have Julien Simon, Chief Evangelist at Hugging Face, to discuss generative AI with Hugging Face. So thank you, everybody, for your patience, and I guess we can go right at it. Julien, all yours.
All right. Thank you, Alex. Let's get started. So hi, everybody. My name is Julien, and I am the Chief Evangelist of machine learning startup called Hugging Face. And if you've never heard about us, I guess I'm going to fix this. So let me share my screen, and we can get started right away. Whoops, and I should start on the first slide. Yes. Here we go. Okay, so that's us, Hugging Face. We have a cool logo. Everybody likes it. If we meet on the road, ask me for stickers, right? And you can put that emoji everywhere. I guess by now it's pretty clear that transformers have become the de facto architecture for deep learning tasks since the dawn of BERT and the many transformer models that followed. We've seen traditional architectures like CNNs, LSTMs, RNNs being pretty quickly replaced because transformer models were so much more efficient at natural language processing and computer vision and audio and speech and a whole bunch of different things. So that's really the situation now. A lot of you are certainly working or experimenting and I guess maybe even deploying transformers to production. And it's simply because they just work better than the previous architectures. But the wheel keeps spinning, and now it's 2023, and it looks like transformers are, a household name already. And now we have to face this new wave of generative AI, which is even faster than the transformer wave. It's disrupting industries and finding its way in production even faster than the NLP transformer models did. And proof of that is how many of those models are actually in production these days. I don't think I need to mention ChatGPT. It's obvious. We've also seen generative AI models used for code generation, coding assistance. GitHub Copilot, Amazon Code Whisperer. Obviously, those models have been heavily used for image generation with stable diffusion models, and now the integration of similar models into the Adobe tools. And even in more traditional industries like financial services or CRM, we see companies like Bloomberg or Salesforce and others training their own large language models from scratch and deploying them for their own customers. By the way, Bloomberg is one of our customers, and I think there is a Bloomberg session this afternoon as well. I would highly recommend that you watch it. It's certainly going to be fascinating. So Hugging Face, where do we stand? Well, Hugging Face is trying to do two things. The first thing, I guess, is we're trying to make state-of-the-art models accessible to everybody. And the second thing is we try to make them accessible in the simplest possible way and using open source, right? So if you want to summarize Hugging Face, I guess you could say open source, state-of-the-art, and simple, right? And these are the three things that I guess make us popular. And we've built and we keep building the largest collection of open source models. They're hosted on our website called the Hugging Face Hub. And I think as of today, we have a little more than 260,000 models. That slide is never up to date. And that's great, I guess, because it means the community keeps adding models. We have over 45,000 data sets, and all those are open source, although they do come with different open source licenses. So please be mindful of that. And those models come from literally everybody, you, me, all the way to large tech organizations like Google and Meta. And yes, we do have some OpenAI models, although I wish we had more. And literally everybody in between, startups, research projects, universities, etc. And so that's why you get so many models and data sets, because literally everybody is sharing them. To give you a sense of the traffic we have over 500,000 users every day and multiple millions of model downloads every day and growing. So thank you, everybody, for making us successful. And please keep sharing models and data sets. If we zoom out and try to look at Hugging Face, obviously we have models and data sets. They wouldn't be too useful if we also didn't have open source libraries like transformers or diffusers. And those libraries make it very easy to download the models, predict with them, fine-tune them, etc., etc. So there's a whole collection of open source libraries. Go check out our GitHub organization. You'll find more. And we've also built Spaces. And Spaces, which I'm sure you're familiar with, is a way for the community to host machine learning applications to showcase their models in a simple web app, which makes it easier to demo and explain what those models do in a web context instead of running them in a Jupyter notebook, which never really works especially with non-technical folks. So Spaces are hugely popular. Again, you can create your app in minutes and host your model there. When it comes to deployment, obviously you could deploy anywhere on any service because it's all open source, but we've also built two services. There's a free service called Inference API. As you would imagine, it's limited in compute terms. And if you want production grade deployment, you can use Inference Endpoints, where you can one-click deploy any model from the hub to AWS or Azure with auto scaling and security all the way to private models, etc. So this is probably the Hugging Face you're familiar with, but that's not it. We've also been busy training models. Last year, we published Bloom, our open source alternative to GPT-3. This year, we published StarCoder, a 15 billion parameter model for coding assistants and coding conversations. And we've also built Hugging Chat, which is a fully open source chat application using the best open source models out there. And I guess we'll take a look later. But that's not it, because our users run Hugging Face workloads everywhere. And so we're very keen on building the best Hugging Face experiences anywhere our users are. And so we have cloud partnerships with AWS, Azure, and IBM, working with those companies to integrate Hugging Face into their machine learning services, making it hopefully seamless to train and deploy models. And last but not least, we also have hardware partnerships with Intel, AMD, Habana, and AWS for their custom chips, Trainium and Inferentia. And here the game is really to work with those companies to make sure we can train and predict with our models as fast as possible, and leveraging the hardware acceleration features present on the underlying chips, right? So there's quite a bit going on, you could say. The last thing I want to mention is we have a consulting and professional services program called the Expert Acceleration Program, or EAP in short. And well, we can help literally from A to Z, whether it's building data sets or finding the right model to use, or fine-tuning it, or running maybe initial training in the most efficient way, selecting parameters, evaluating model quality, optimizing model performance in production, because we're doing all of this ourselves, right? And we can leverage all the experts inside the company, from the science part to the ops part, and help you get to production very quick, without falling into the, I would say, the common pitfalls that you're likely to encounter when you start working with those models. So get in touch. We'd be happy to discuss and see how we can help. We have a particularly strong partnership with AWS. So pretty much everything I mentioned before is available on AWS. So we do work on the infrastructure side, optimizing for all the hardware platforms that AWS offers. We focus heavily on Amazon SageMaker to train and deploy Hugging Face models in the best and easiest way. But we're also providing tools for EC2 users, and we're currently working on integrating the spaces and the inference endpoints on the Amazon Marketplace, where you can already find the EAP. So that as an AWS user, you can just go to the Marketplace and purchase those different products without having to engage into any kind of sales discussion with us, making it generally faster to experiment and deploy those services in your own AWS account. So I guess the first big topic I'd like to address is, why would customers even be interested in open source models? What do our customers tell us? Well, obviously, they love the accessibility. They love the fact that they can use the models regardless of budget or affiliation. You can download any one of those models in one line of code and start working with it, experimenting with it, whatever, immediately, right? And of course, for free, right? The next thing they love is the transparency, right? The models are open source, which means the architecture is fully visible. You can inspect it, load it in PyTorch and TensorFlow and see what the model is. All the weights and model parameters are accessible. In a lot of cases, there's good information on the training data that was used. Sometimes these data sets are even fully available on Hugging Face as well, so you could even replicate the training yourself, etc., etc. The next thing they like is, of course, privacy, because when you work with open source models, you simply don't have to send your data to closed models and black box APIs, and you don't have to worry about what the privacy policy says, assuming there is one. Intellectual property protection is very important to our customers, because they have high value data, and if they train models, open source models, on that data, then those models become their models. So they're very keen to understand what happens to those models, who owns them, who can see them, who gets access to them. And again, if you work with open source models, there's no question. Those models are hosted on your infrastructure, whatever that is, and so there's no risk. Freedom of choice. We have tons of models, and as we'll see in a few minutes, the state of the art moves very quickly. So you may be tempted to switch from one model to another one to get the best performance. And so with open source models, you can easily do that. You're never locked in. And finally, you can train and deploy models anywhere you like, from your laptop to on-prem to cloud to anywhere. Use any environment, use any infrastructure, use any compute service. The choice is yours. We're also hearing from customers that they prefer to work with smaller models. So let me explain why. The first thing is a lot of enterprise use cases are actually quite narrow compared to trying to answer every single question about the universe. So it feels pretty intuitive that if you have a smaller problem, then you could certainly get the job done with a smaller model because the domain is just simpler. Obviously, agility is critical. A smaller model means faster training time, faster retraining time, and you can just iterate quick and discover your problem quicker and upgrade your model quicker when you need to. Costs, for the same reason, a smaller model is much less expensive to train and host. And over the lifetime of your project, this is really important, especially inference. Speed is something that people are learning as well, as they're sending huge context to some models. That, well, the smaller a model is, the faster it predicts, right? So if you have a latency sensitive use case, a smaller model could be a good choice. And last but not least, accuracy, because as shown again and again and again, a smaller model fine-tuned for a particular purpose will almost always, and I would strike almost here, I think, outperform a larger general purpose model, right? That's just the way it is. A custom tool is always better than a Swiss Army knife. And in fact, if you look at the models on the hub, you'll find a lot of models come in different sizes. Here you can see the FLAN T5 models from Google. The smallest one is 80 million. The largest one is 11 billion. So, the chances are you can just start small, evaluate, and scale up only if needed. So let's look at some of the cool models that came out. And it feels like these are, again, old models already, even though they're only a few months old. So I think by now everybody has heard about Llama, which really kickstarted another revolution within the revolution. And we saw Alpaca from Stanford, starting from Llama, and Koala from Berkeley, again starting from Llama, and improving on the baseline models and getting dangerously close to OpenAI performance. And obviously the Google models, the FLAN UL2, which are the latest evolution of T5 models, which are amazing for things like summarization and Q&A, etc., etc. So these are models literally from February and March. And then a few months ago, we all heard about Falcon. And Falcon was the new sheriff in town, a 40 billion parameter model trained by an Abu Dhabi team, trained on AWS, I believe. And this was the best. And I said was because there is I guess a better one now. But you could, within days of the model release, it was supported in the Transformers library, and you could deploy it on high inference endpoints, and you could fine tune and deploy it on Amazon SageMaker. And again, I don't think there's any other place and collection of tools where that was the case. So working with the Hugging Face set of tools is generally, pretty efficient. And so literally 2 days ago, it was July 18th, Llama 2 hit the streets, and Llama 2 is even better than everything else. And I guess now everybody's rushing to test Llama 2, which is fine, because 2 days after its release, it is supported by the Transformers library, inference endpoints. It's also available in Hugging Chat, so you could select Llama 2 in Hugging Chat and give it a try, and obviously Amazon SageMaker. So again, just to show you how quickly those models are supported, by Hugging Face, thanks to the community and the additional work that we do on top of that. And obviously, when you see that fast pace of innovation, the main question I get from customers is, how do I pick one? Right? How do I know which models, which LLMs I should start from? And to help clear some of the confusion, we've created a leaderboard, and you can find this as a space on Hugging Face, where we score all the open source LLMs on different benchmarks from Eleuther AI. And in a nutshell, those give you a sense of the model performance from zero-shot prompting to many-shot prompting. From some use cases, you could need one or the other, and there are some differences. So make sure you look at the actual benchmark that best reflects your use case. And so we can see the leaderboard, and there's a whole wave of Llama models, Llama 30 billion, Llama 270 billion, etc., etc. And this, if we meet, a couple of weeks from now, I can guarantee the leaderboard has changed again. So it doesn't necessarily mean you should always jump to the latest and greatest, but at least you can compare the model that you use today to the state of the art and see, how far it is from that, and whether it could make sense to actually switch, and what the associated cost of that would be. But I think this is a good place to keep an eye on and see how fast things are moving. There's you can see there's a thing called performance benchmarks here, and this is more recent. This is the similar effort on giving you information on throughput for the models, right? So which models helps you get whatever throughput, prediction throughput your app actually needs. So lots of new dimensions to this. So once you've picked a model, I think you could say, well, how do I train it, and how do I fine tune it, yes or no? And I think there are a couple of things that you need to know here. So I guess the common knowledge for a few years has been that having larger models helps get better performance, right? And yes, OpenAI certainly made sure we all heard this. The problem is a lot of folks stopped there. And there was this amazing paper in 2022 from DeepMind, the so-called Chinchilla paper, named after the model presented in the paper, where the DeepMind teams actually showed that a lot of LLMs are undertrained. So they're trained on too little data. And given how much time and money you spend on training them, they underdeliver, right? So you literally burn your training dollars away for very, very, very diminishing returns. And the thing that should be done instead is scaling the model size and the data set size linearly. Meaning, if you want to train a model that's twice the size, you need twice the data, right? And typically for models like GPT-3 and I guess our own Bloom model, that wasn't the case. We grew the models faster than we grew the data sets. And to prove their point, they trained their famous Chinchilla model, which is 70 billion, on a much larger data set of 1.4 trillion tokens, so about 4 times the size of the GPT-3 data set, and they completely outperformed, right? And we've seen more examples. So Bloomberg, which I mentioned, followed exactly the same approach, starting with the Bloom architecture from Hugging Face, resizing it to 50 billion, because that was the optimal size given the compute budget they had and the data set size they had. So again, I'm sure it will all be explained in their presentation. And the recent models, Falcon and Llama 2, have been trained on even larger data sets, even though they're not really bigger models. So I think goes to show, it's not about the model size, it's really about the data set size and, of course, the data set quality. So I guess the conclusion of this is, training large models is a cost, and building quality data sets is an investment. And again, you can see the pace of innovation, and you'll certainly train much more than you thought, right? Because you want to keep up with state-of-the-art. No one wants to be stuck with a model that was great a year ago. So if you work with models that are unnecessarily large, you will repeatedly train them or fine-tune them and waste time and money because, again, of those diminishing returns. So instead, you should really find the smallest model that gets the job done. And I think the leaderboard will help you do that. And if you right-size your model, not only do you spend less, but you also get faster ROI because you spend less on training and inference, and you create business value quicker. And so it also makes those models easier to discard should you decide to replace them with another state-of-the-art model. So instead of spending too much money on training, you should spend as little as possible and invest those savings into building high-quality data sets because they will pay dividends forever. If you have healthcare data from 30 years ago, it's still good. If you have stock market data from 30 years ago, it's still good, right? And I could continue giving you examples. So models are transient and expandable. Don't fall in love with them. Instead, fall in love with the data and take good care of it for decades. Another thing I'd like to discuss, going on with that theme of being as efficient as possible, is there are a lot of technical features out there, like mixed mode training and quantization and smaller data formats, etc. And they can make a huge difference in training times and inference time. The problem is those techniques are arcane and they can be difficult to use. But again, in the spirit of making things much simpler, we've integrated them in the Hugging Face libraries. So Optimum, which is our library dedicated to hardware acceleration for training and inference, leverages the underlying hardware almost invisibly. We have a library called PEFT for parameter efficient fine-tuning, which again makes it very simple to fine-tune models on a limited number of parameters and getting extremely close to the accuracy you would have gotten from a full fine-tuning. We have a reinforcement learning library called TRL, built by the community and supported by Hugging Face. And all those tools follow the same principles, which is implement state-of-the-art techniques that make it simple. And here's an example, right? So here's Llama 2 7 billion fine-tuning. Yes, there is a vanilla script to do this. So run that script from the TRL library on whatever data set you'd like to fine-tune on. You can do 4-bit quantization, and you can do parameter efficient tuning just like this. And this example runs on a T4 GPU, which only has 16 gigabytes of RAM. So that's the impact. You can work with very small GPUs. I think this is even available on Google Colab. So you could fine-tune Llama 2 in Google Colab, right? I don't think you thought that was possible. So a few more examples before I close. This is a bot we built called Stack Llama, and it was fine-tuned on, it's a Llama 7B model, Llama V1, fine-tuned on the Stack Exchange Q&A dataset, so programming questions. So what is really interesting here is the blog post actually details all the steps. How did we use reinforcement learning with human feedback, with the TRL library, et cetera, et cetera. So if you've looked for a while for a walkthrough, a detailed walkthrough of training an RLHF model, this is it, right? Stack Llama, amazing blog post. Here's another one. So this is the only live demo I'm going to do, and it's going to be really quick. This is QA chat, and this is a 7 billion Mosaic ML model. So let's ask it a question, right? I want to know about the Tour de France. Okay, all right, and it's going to give me some answers. Okay, fine. Well, you can say, what's the big deal? Well, the big deal is this is a quantized model that runs on a single CPU, right? And this is pretty fast. And this is really generating faster than I can read. So let's try another one, right? There we go. So this is what you can do if you do the homework and you work smart. You start from those large models and optimize them and run them on a single Intel CPU, right? And you heard that right, CPU with a C. All right, a few more things. Of course, Hugging Chat. Go give it a try, huggingface.co/chat. Originally built on the Open Assistant 30 billion model as of, I think, yesterday. It also supports Llama 2 70 billion. And here's a silly example where I'm writing a promotional email to myself, and this is the Open Assistant model, trying to get me to go check out the latest bikes at the dealership. And this is really something I wrote, almost in one go. And the answer I got was pretty good. I mean, I wouldn't mind receiving that kind of email. It was pretty good. So generating content, generating emails, there you go. It doesn't have to be more complicated than this. StarCoder is, like I said, a code generation model. We have a VS Code plugin. You can see it in action here. The model is also surprisingly good at coding conversations. So if you need, I guess, a second opinion, coding buddy, you could try that. I had a really good conversation or two with StarCoder. Again, all open source and all free and simple to use. Text to image. How could I not show this? So we're all familiar with Stable Diffusion, right? This is the example that I've been showing for a while. Stable Diffusion 1.5 from October 2022. Use the diffusers library, create a Stable Diffusion pipeline, prompt it, generate an image, save the image, and this is a pretty good one, right? And that's all there is to it. So if you need to generate content for, I don't know, blogs or marketing posts or anything else really, or if you want to generate synthetic data to augment your data sets, that's a very simple thing to do. And well, just I guess a few weeks ago, we welcomed Stable Diffusion XL on the hub. And again, you can go and try it, and you can see this is the exact same code. So I guess I'm only changing the model name here. So this just goes to show if you work with those transformers and diffusers library, the code is not going to stand in the way. It's very little code. It's stable code across releases and models, and you can very easily upgrade your apps and workflows to the latest and greatest models without having to rewrite anything. And this is a really, I guess, a much better generated image. It has this, photographic quality that the previous one I don't think had. All right, so summing things up, transformer models, and I should say, I guess, diffuser models as well, are the de facto standard for AI apps at the moment. So if you've never looked at transformers and diffusers, well, it's never too late, but you should do it. Don't believe the hype. Today's best model will be superseded in weeks, and I guess this prophecy has been proven right once again with, I guess, Falcon losing the top spot to Llama again, right? And maybe Llama 70B will be replaced too. In fact, I'm sure it will be. No model rules them all. That's a fallacy. There is no model that works well across all languages, across all industries, across all use cases. Sorry. And so you have to find and potentially build the most appropriate one with the highest performance for each use case. What we hear from customers is that right-sized, optimized open source models are the way to go. I'm not saying there are no other options. I'm saying this is what our customers are using, and this is how they find success. And last but not least, at the moment, we're very happy with the work we're doing with all our cloud partners, but at the moment, AWS is really the best place to train and deploy Hugging Face models, thanks to the joint work that we've been doing with them for over 2 years now. So if you're an AWS user, I think you're in a good place. If you're not, it might be worth checking them out. You could save a lot of time and energy there. Final slide. getting started, some good links from, I guess, beginners to more advanced users. So take a screenshot. I will share the slide with ODSC, so you can obviously get all of that. If you'd like to get started or keep up with the crazy pace of Hugging Face and LLMs, these links will help you do that. Well, that's really what I wanted to tell you. So I would like to thank ODSC once again for inviting me. I hope this was useful, and feel free to get in touch on LinkedIn or anywhere you can find me if we can help you get to production quick. Thank you again, and enjoy the rest of the conference.
Thank you very much for your presentation, Julien. ODSC is always happy to have you. And that leads us into our next session. All right, our next session is with Zhang, how to train your Vicuna, fine-tuning, serving, and evaluating large language models in the wild. And as a quick reminder, this week is our last week for 70% off ODSC West tickets. So if you're interested in joining either in person or virtually, make sure to get your ticket by tomorrow. And with that, we are over to Hao. Hao is currently an assistant professor at the University of California in San Diego. He is working on the ALPA project and the SKY project, aiming at democratizing large models like GPT-3. He is an assistant professor at a Data Science Institute and Department of Computer Science Engineering affiliate at UC San Diego, and his research is primarily focused on large-scale distributed machine learning in the joint context of ML and systems concerning performance, usability, cost, and privacy. And with that, we are over to the speaker.
Hi, thanks. Thanks, Alex, for introducing me, and thanks ODSC for inviting me to give the talk. And my name is Hao, and I'm currently an assistant professor at UCSD. And I also previously I worked at UC Berkeley with a few folks, and we together founded the MSys.org, in which we train large language models, and also we share technologies to serve or deploy or evaluate large language models. So today I want to give you guys an introduction about our work in the past, say 6 months, which is the open source large language model called Vicuna. Yeah, let's get started. So before we introducing Vicuna, I want to give a little bit background. That is the Llama and the Llama 2, which was released just 1 day ago, 2 days ago, actually. So basically, this year, I think Meta has been very generous, and they released the pre-trained large language model with Llama to the public. And the key observation here is that before Llama, I think people focusing on scaling models. So the model set has been increasing quite a lot. But after Llama, during the development of Llama, I think people start realizing we can scaling data and model together to follow the Chinchilla scaling law. And without like scaling a model into a size like several hundreds of billions, we can still get a quite decent performance on smaller large language models, such as the Llama 13 billion and the Llama, for example, 65 billion. And also Meta has been very generous to make this model with publicly available. And that is certainly very, very good news to the open source community. So the original Llama and Llama 2 models are just plain large language models, which means that they are strong, but not that useful because, for example, they cannot actually follow human instructions. Since Llama models were made public, the open source large language model development have become very, very active, and we can almost see daily updates from open source. Like the updates will be something like a new model is fine-tuned from Llama for certain tasks. So among all these models, one of the most notable models is the Vicuna we tuned at the MSys.org, which even by today is still considered as one of the best chatbot models fine-tuned from the Llama-based models. So in this talk, I'm going to share our experience in fine-tuning and serving this Vicuna chatbot model. But before that, I want to first show some of the impacts we have made by doing this project and some follow-up works. So basically, we developed the open source project Fast Chat, which supports the Vicuna, and this project has accumulated almost 25,000 stars on GitHub. And we also deployed the chatbot Reina project, where people can chat with a lot of open source models on our website. And this website actually receives quite a lot of traffic, like a daily traffic of 40K chat sessions. And we also published a chatbot Reina leaderboard in which we evaluate the large language models available in the market. And I think a lot of people use our leaderboard as a default to go places to see which model is better or which model is more suitable for their tasks. And one joke I want to make is because of our development and also a few other open source models, I think there are some very interesting documents or public blog posts stating that we have no moats and neither does OpenAI in terms of large language model development, which I don't quite agree. So that being said, I want to start sharing. I want to start an agenda with this talk. So basically, in this talk, I'm going to I'm going to briefly introduce how we get to Vicuna from Llama. This part actually includes how we prepare the data and how we do the training. And this part is actually very, very easy and simple, but the results are very impressive. And then I will briefly talk about how we evaluate this open source large language models, which turns out to be very, very difficult because it's a very open domain chatbots and it can finish a lot of tasks which will break a lot of existing academic benchmarks. And finally, I'm going to spend probably half of the time talking about how we serve these models in the chatbot Reina, which I think a lot of industry practitioners care a lot because it's directly relevant with their cost. So I think one magic secret sauce we found for Vicuna is we found this website called sharegpt.com. And this sharegpt.com was developed by a developer who is not in the area of large language model. And in this website basically provides a Chrome plugin where you can install into your Chrome. And once you install that plugin, whenever you chat with ChatGPT, there will be a button on the side, and you can choose to share the conversation to this website called sharegpt.com. And we found this website, and we crawl all the shared conversations from this website, and we eventually get about 70K conversations, which is 800 megabyte disk size. And this is basically our training data. So after we use this data to train Vicuna, and after we realized that the Vicuna performance is very, very impressive, we actually did some retrospective thinking about why this data is so effective, because there are a lot of other community or people who also use ChatGPT data to train their model, but it turns out that our model is always like better. I think one potential reason is like you can consider when people would like to share the ChatGPT conversations, right? It is certainly because that they like the conversations and they find that that particular conversation to share is very, very interesting. I think this ShareGPT actually designs a very, very good mechanism for people to share the highly ranked conversations from ChatGPT, which means that the data quality in ShareGPT.com is much higher than you just plainly distill from other language model or just plainly connect data, conversational data from other sources. Yeah. And once we get this ShareGPT conversation data, the training is actually very, very simple. We just do standard instruction fine-tuning, which means that we do regular language model training with the Lex token prediction loss, but we only calculate the loss on the assistance output, as this figure shows. So in this figure, which means that in this figure, we use the black text as the training data, and we try to use the black text to print the green part of the text. Yeah, and for example, in the first iteration, we all try to put the text from first row to the second row to the language model, and we try to predict the assistance outputs. And once this part is finished, we put the green text again into the prompt, and we predict the next part of the green text. Yeah. And this is actually, if you follow this procedure precisely, you can actually get Vicuna as well. Yeah, very simple. But once you get Vicuna, actually, one core problem we are facing is how we can evaluate these open source language models. One problem that we have been seeing is traditional NL benchmarks are actually insufficient to evaluate today's large language models' conversational ability. So what are the reasons? The reason is actually quite simple. So most of the existing traditional NL benchmarks, they focus on evaluating the core capability. For example, whether the language model can write precise code, whether the model can do text completion, or whether the model can perform like math or some sort of reasoning. And all these are actually evaluating core capability of the model. But in the chatbot scenario, there's another factor that is very, very important, which we call human preference. For example, this includes, for example, whether the chatbot model, the language model-based chatbot model can precisely follow human instructions and try to be helpful to humans, right? And whether their answers are helpful. For example, instead of this slide actually give an example. So basically, in this example, the user asks a question, and the two assistants try to provide the answers. And actually, the answers, in terms of the accuracy of the answer, they are equally good, which means that if you put these answers into traditional academic benchmarks, I think they will be they will get the same score. But in our experiment, we found that many people would favor the response from assistant B because it is more helpful. It shows stronger human preference. For example, it not only gives the precise answer, it also tries to explain how the answer, how to get an answer, and what's the logic or reasoning behind it, right? So, which means that in order to evaluate today's large language model, we need to also factor in the human preference. So basically, in our evaluation of the core question we try to ask is, how can we evaluate human preference? And this question is actually quite simple. The gold standard to evaluate human preference is ask human to read these chatbots, right? Very simple. But the problem is how we can quickly collect these humans' ratings for chatbots, right? I think a lot of large language model companies, they just hire people and pay their salary to read these chatbots. But as an open source developer and as a small community, as a university, we don't have a lot of like budget to cover this part. How can we do this? So the project that we launched to connect with human preference is called Chatbot Arena. And this Chatbot Arena is still live. And I gave the link on this slide, and you can try it yourself. And as you can see from this slide, this Chatbot Arena actually presents to the users a panel. And this panel has two parts. And basically, this panel presents two chatbots simultaneously to the users. And the names of that two chatbots are hidden. And the user can type a prompt, and that prompt will be sent to both chatbots, and both chatbots will try to provide an answer to the same question. And then there are 4 buttons at the bottom of the 2 panels, and we ask the users to rate which answer is better, like which answer they prefer. And unless you click one of the buttons, for example, A is better or B is better, the name of the chatbot won't be, won't be revealed. So basically, this is a very small procedure. We try to gamify the process of collecting human votes. So a lot of people are interested to know like which model, what are the models name, which model actually gives my answer. So they have the incentive to contribute their vote. And by actually launching the Chatbot Arena for about like I think 2 months, and we are able to connect a lot of these votes, and these votes are actually binary. That is, it tells which it tells which model gives a better answer for a certain prompt. And apparently, with this voting data, we can calculate the win rates among all the models we evaluated. And this slide actually gives you a snapshot of the win rates, how it looks like. And with the win rate data, we can actually start adopting some other mechanisms, such as the one recognized or acknowledged by many games. For example, in Go and in many mobile games, people also compete with other players, and they try to get a ranking for to tell the performance of each player. and this ranking system is called ELO. And with the run rate data, we can also calculate the ELO scores of each chatbot model, and it actually result in the red part, the red leaderboard shown on this slide. And as you can see, this ELO score are purely based on human votes. So there's no other like factors, for example, data contamination or any other sort of issues about existing academic benchmarks. Yeah. And actually, since we launched this chatbot arena, this ELO leaderboard has become a to-go place for many like industry practitioners. They come to our website and see the ELO of each chatbot, because I think this ELO has a lot of unique advantages shown on this table. Like in this table, we compare the different large language model benchmarking methods, and as we can see, this chatbot arena shows a lot of unique advantage. For example, its question sources are uncontrolled, which means that the user can type any type of questions to ask different pairs of chatbots and try to get an answer. And these evaluators are also purely based on human, which means that it accurately and only reflects the user preference, which I think a lot of people care a lot when developing their chatbot applications. And also the metrics is a very well acknowledged metric, ELO ratings, right? It has been adopted for many years in many other games. Yep. So that's our way of evaluating this large language model chatbots. And if you are interested, you can go to our chatbot arena and try to browse and leaderboard. And after launching this chatbot arena, we start realizing actually this problem is more than just designing a voting mechanism, but also serving like many models on a small cluster. So what are our deployment goals here? So in order to connect enough users' voting data, we have to serve all those models like people care about simultaneously in this chatbot arena website, right? We need to guarantee high throughput and low latency, because if its performance is too bad, I don't think people will come to us and play with this chatbot arena. And in reality, we are a university group and we don't have a lot of resources. So our cluster is a university sponsored cluster with 20x A100, each with 40 gig memory. And in the first week we launched Vicuna, we only served one model, Vicuna. But after we launched chatbot arena, we gradually increased the number of models to be served to 20 or even more. And also we receive a lot of traffic because we need to serve many users and try to collect votes. And this actually poses a very significant problem to us. That is how we can efficiently perform inference and serving for autoregressive LLMs with limited resources, right? And I think this problem is probably one of the most important problems in 2023, the LLM era, because how to perform. Because this is really a problem that everyone cares about now, because it will largely impact how much money you pay, right? Your cost if you are trying to host an LLM service yourself for your clients. Yeah. So the answer we give is that we can try to use. We developed a new project called VLLM as a backend, serving backend, and this VLLM is featured with a key technique called page attention, which can reduce the serving cost a lot. And in the rest part of the talk, I'm going to focus on introducing this page attention and VLLM. It will be a little bit more technical than the first part. Okay, so to understand the autoregressive inference, let's look into the inference process of LLMs. So first, the user prompt provides a prompt consisting of multiple tokens when they use LLM, right? And in this example, the prompt is artificial intelligence is, and the prompt goes through the model, and then we get the next token to the prompt, which the model predicts as the token 0. And in the next step, we feed this new token back to the model and get the second output, right? Which is future. And this process is repeated until the sequence either reaches its predefined maximum length. For example, in Llama, this maximum length is 2K and Llama 2 is 4K. Or it generates a certain token called the end of sequence, which actually signals the model that, okay, I'm finished. So in the inference process, LLMs have a unique component compared to any previous models, which is often called QWAK in the ML literature. And So in processing a new token, the model actually needs not only the representation of the current token, but also the representations of all the previous tokens, that is the QWAK. So these states of previous tokens should be kept in memory, and this is the part that consumes a lot of memory when you perform LLM inference. So the same for the next step, except that the input token in the previous step, which was newly appended to the QWAK. That is, every time when you generate a new token, you have to append its QWAK to the QWAK pool, and when you predict the next token, you have to access the pool, the QWAK pool. Yeah. So to recap, the QWAK is a memory space to store intermediate vector representations of tokens. While the name is a little bit misleading because I think a catch is has special meanings has the designated meanings in computer science. But you can think of this as a working set of a sequence rather than a catch, because the model uses every previous token state to generate the next token. And importantly, the size of QWAK grows as new tokens are appended, and it also shrinks as the tokens are deleted once the sequence finishes. So here, so given this QWAK story, so here the key insight of our project is that efficiently management of QWAK is very, very important for high throughput LLM serving. So let's say we run a 13 billion model like Llama on a A100 with a 40 gig GPU memory. So the model parameter takes roughly 26 gigabytes of memory. And in addition, a small fraction of memory is used for workspace, and the rest of memory can be used for storing QWAK. And our finding is that existing systems use QWAK very, very inefficiently, and thus significantly limited number of requests that can be batched together. So in contrast, our solution, WLM, manages QWAK efficiently and thereby allows much larger batch size with the same amount of memory. Yeah, so basically existing system are this orange curve, and our system is this blue curve, and our system can effectively flatten the growth rate of the QWAK space. So we can use a much larger batch size, and as a result we can increase the we can use a much larger batch size, and as a result we can increase the throughput, because in GPU when you have a much larger batch size, you can always compute faster, right? So what are the memory inefficiencies in the previous system? This is a snapshot of the QWAK when using a previous system, and where we find 3 types of memory waste. The first is a reservation, which means that the slots that are not used at this moment, but will be used for the sequence in the future. So here the 3 slots in the middle are reserved because they don't store any token at the current step, but will be used to store output tokens in the subsequent steps. And the second is the internal fragmentation, which means that the slots allocated for a sequence but never used. And this happens because the output length of a sequence is not long before. And finally, external fragmentation happens because the different requests A and B may have different sequence lengths. So the memory waste is significant. In our profiled data with different memory management schemes, we observe that only 20 to 30% of the QWAK is actually utilized to store the token states, and the rest of the space are just wasted. And in contrast, in our new project, new backend WLM, we achieve over 96% of average utilization of the QWAK memory space, which is several times higher than the existing systems. So the way WLM solves this problem is to employ an old idea of the virtual memory and paging in operating systems. So as we all know, OS uses paging to reduce fragmentation in the physical memory space, and uses virtual memory to efficiently and elegantly space multiplexing between processes. And what WLM does is basically very similar. So it uses a similar kind of idea to resolve the fragmentation in the QWAK and enables efficient space sharing between requests. This is enabled by our new technique, page attention. Let me introduce this page attention. So to begin with, we partition the QWAK into an array of token blocks. And a token block is a fixed size chunk of memory that can store token states from left to right. And in this particular example, the block size is 4, which means that we can store 4 tokens in a block, right? And again, the tokens here are not strings. there are token states, and each token state is actually maps to like for example in PyTorch it is a PyTorch vector, yeah, like this. Like each token will have a vector representation. And on top of this, we introduce page attention, our new implementation of attention mechanism. And we find that the fundamental limitation of the previous system is they require all key states for a sequence to be stored in a continuous memory space. And this is a convention in typical DNN workloads where the input-output space are static. But however, it turns out that to be highly inefficient for inference, where the sequence lengths are highly dynamic and unknown. And page attention directly addresses limitation. And with page attention, the key states can be stored in non-continuous blocks located in arbitrary position in the key cache. So we virtualize the key cache to logical and physical token blocks. So let's see how it works with an example. So request A, it comes with a prompt. Alan Turing is a computer scientist. And in the logical view, where the tokens are stored in consecutive blocks and their orders is preserved, right? But in the physical view, on the other hand, the tokens in the same sequence may not be stored in adjacent blocks, and the orders between the blocks can be arbitrary. And the mapping between the logical blocks to the physical blocks is stored in a block table, which we created as a sort of paging mechanism. Yeah. And let's continue this example. And let's see the model has generated the next token end. And the new token is first appended to the last logical block, which is the block 1 here. And using the block table, we also append the new token to its corresponding the physical block on the right, right? And the same for the next token mathematician, right? And finally, if the last block is full, which means that block 1 is full now, then we ask the system, the underlying system, to allocate a new physical block and store the token in the first slot of this block. Like this, yeah. And this is basically how VLM manages the key cache. So far we have covered how it works for a single request, a single sequence. But you can imagine how it is gonna work for multiple requests processed at the same time. Basically, we allocate different blocks for different requests, right? And each block are separately managed in a virtual space and a physical space, and there's a block table linking them. Let's quickly analyze the memory efficiency of VRM. So first, VRM has minimal internal fragmentation. This is because the internal fragmentation only happens at the last block of the sequence. And this means that the number of the wasted tokens per sequence is bounded by the block size, which is very, very small. And in practice, the block size is much smaller than the sequence length, which is totally acceptable. And second, VRM does not have any external fragmentation since all blocks have the same size. And putting this together, VRM achieves very, very high utilization of key cache. We observe like over 96% on average. And apart that, the VRM also supports is we can use this page attention mechanism to enable a lot of sharing, which are very, very commonly seen in LLM generation. For example, in many LLM applications, the user will request an LLM to generate multiple response for a prompt. And the VRM can support this kind of parallel sampling, beam search, or like prefix sharing, all this kind of VRM apps pretty well. Yeah, but in this talk, due to time limit, I'm going to skip this part. So we implement this VRM as an end-to-end serving system and includes the front-end distributed model executor and scheduler. And more specifically, we implement the VRM based on PyTorch and Hugging Face transformers, and we use Ray and Megatron for distributed execution. Yeah. And if you're interested in the code, you can go to the repo to check it. And for now, VRM supports a lot of models, including our own Vicuna, and also including many other popular models. For example, the Star Coder for coding. And the source code is released at the link I posted on the slide. And actually, we got a lot of stars within 4 weeks. And we also got a lot of adoption. Our partner, Hugging Face TGIZ, since we released the VRM, they immediately send on people to integrate this page attention into their TGI library. We also get a lot of adoption from other universities. And to see how we're on performance, so we can perform some evaluation. So we just evaluate the throughput, for example, how many requests you can serve in given time, and we compare it to a few baselines like Hugging Face, TGI, and also the previous state-of-the-art, which is called Orca, which is not open source. And we use the data from ShareGP and Alpaca. And as you can see on both figures, VLM, the blue curve, returns much higher request rates than other baselines will maintain low peak per token latency. And when we bound the per token latency to like 100 microseconds, VLM achieves 6 to 13x higher throughput than Fast Transformer by NVIDIA, and 1.7 to 2x higher throughput than Orca. And the gain gets larger for like parallel sampling or parallel generation apps such as beam search. Yeah, as you can see from this slide. Yeah, as the beam search width increases, and our project VLM also achieves higher performance compared to Orca, up to 4x. Cool. We also compare our project to Hugging Face GGI before the integrated page attention, and it shows that we are 24x higher throughput than the original Hugging Face, and we are about 3.5x higher throughput than the text generation inference engine by Hugging Face. And we deploy this VLM project in the Chapel Arena and Vicuna fast chat library, as I mentioned before, and it has been deployed for 3 months, and it is able to handle average traffic of 40K conversations per day, and it reduces the total number of GPU we used at the MSS.org to serve the Java Arena by 50%, and while still serving 2x and 3x more requests per second. So to summarize, in this VLM, we modernizing virtual memory in OS for memory efficient ARM serving, and that's pretty much this wrap up this part of the talk. And so I give a very brief overview of what happened in the past 3 months in MSSR. So basically, we developed the Vicuna model. We evaluated the Vicuna model using a Chapel Arena, and the backend engine that is enabling this entire story is called VLM. And you can feel free to check out our projects, which I give links here. And if you have any questions, feel free to ask. Yeah, thank you.
Thank you very much, Hal. That was a great session. And our next session will begin in a few minutes. So stay tuned for Text to Insights, building real-time analytic systems with generative AI. Start in 3 minutes. Hello, everybody, and welcome to the next session as part of Stage 2 of the Generative AI Summit. I'm happy to welcome Avinash and Dillon, both who work at Databricks. Avinash is a solutions architect at Databricks. His current work involves working with large retail and consumer packaged good organizations across the US, enabling them to build ML-based systems. His specific interests include streaming ML systems and building applications leveraging foundation models. Dillon has spent the last 5 years as a solutions architect at Databricks, where he has an extensive background in working with data engineers, data scientists, and business stakeholders to productionize data and ML projects. He is also active in developing new field projects intended to accelerate the management of data infrastructure. Let's see. And with that, I will present the speakers on text insights, building real-time analytic systems with generative AI. The floor is yours.
Thanks, Alex. Can everybody see our? Oh, great, awesome. Yeah, this is my biggest concern coming into the presentation with or the talk was not being able to share the slides properly. So this is awesome. So thanks for the introduction, Alex. So Dillon and I both work at Databricks, and as Alex mentioned, we kind of have our own spikes. Just to elaborate, my work has mostly been focused on deep learning based projects for the past 2 years at Databricks, alongside helping customers with their entire end-to-end data lifecycle with a specific focus on machine learning. And this project, this type of work where you're trying to generate insights based on natural language input has been a topic of interest for me for a number of years. And I've done a fair bit of work in the past 8 months or so on this with open source capabilities using Databricks as a platform, leveraging GPU compute and so forth. So I'm excited to talk about this and share what we learned so far. But a part of making this sort of project successful is the data aspect of it. And that's where Dillon really comes in. So I'll let Dillon introduce himself and take it from there. You're on mute, I think. Still on mute.
Okay, all right. How's that going?
It's good.
Great. Well, we were having issues backstage, so I'm not sure what switched over. It's kind of funny. Yeah, I think the background earlier was was good, but I spend a lot of time. Basically, my background in data architecture and the processing, data integration, fancy word for ETL and streaming and ingestion and all those things. Basically thinking about how do we make sure that the data is fresh enough for whatever use case it is. I think with generative AI and with all of the implications that are going on in the world right now, I think all of the relevance of data quality and data freshness and all of these different things that we can use to describe data, it's sort of like the magnitude of importance has just increased, but it's always been sort of relevant, if that makes sense. So.
Thanks, Dillon. All right, let's keep going. So the ability to make the data layer accessible to lay people or business users who might not write any SQL has kind of driven entire industries for decades. You can think of the entire BI industry as an example of this. It's several $1 billion in just total addressable market. But literally being able to ask questions from your data and get accurate answers reliably has been the holy grail for a long time. But it has not been possible because of various technical limitations. Here in this example, just to kind of see what we mean, you have someone asking a question, a system, which we can term the insight engine. Then you can do the interpretation of the input, a query execution layer that would run the query, and the same insight engine that can provide the result for the business user in natural language. This is a solution that you can kind of realistically build with LLMs or large language models, but there are some caveats, and that's kind of why we wanted to talk about the data and the systems level architecture for this. and kind of let's see what goes into the process and kind of talk about some of the historical context that will kind of really shape our understanding of how we conceive this solution. So traditionally, people have approached text-to-SQL as a sequence-to-sequence type of problem. So the roots of this entire like boom in LLMs or large language models start with like machine translation research, a field that has close ties to these sequence-to-sequence models. And as a matter of fact, in the original paper about attention is all you need. You know, that wasn't a generative AI paper. It was a machine translation paper by some researchers at Google, and kind of blew up really and caused this entire transformer-based model development. Usually, the class of transformer architectures that are called encoder-decoder models, as you see in the picture, can be useful for these sort of approaches. And historically, the T5 family of models, including the FLAN T5 models, Code T5 models, and as of late, Code T5 Plus models, have been good for text-to-SQL generation. As a matter of fact, the Code T5 16 billion, the Code T5 Plus 16 billion parameter model has shown some really good results. The usual process for these sort of models is to pre-train the model on a large corpus of text data, then fine-tune it on text-to-SQL pairs. So there has been limited success, as I mentioned in the past, but you know it hasn't been kind of considered a universal solution by any means. Now, when it comes to decoder models, especially with instruction following models, with text-to-SQL pairs as the instruction alignment mechanism or instruction alignment data that you use, there has been more success as a matter of fact. So models like GPT-3, GPT-3.5, that's the backend model powering ChatGPT that I'm pretty sure you're aware of. Llama 2, MPT-7B, and then MPT-30B, particularly the instruct models are really good. These models can be fine-tuned pretty well for text-to-SQL generation, and we'll kind of get to the details of how to do that in a minute. But the idea is that you have this pre-trained model, like we discussed before. You kind of pre-train it for predicting the next token on a large corpus of text. It could be the entirety of the internet, which has text that is good and bad. So people have moved towards pre-training these models on much higher quality data that has yielded increasingly good results. When it comes to instruction fine-tuning, you align it for text-to-SQL generation, and this is done in a supervised manner. And this whole process of instruction fine-tuning is called supervised fine-tuning. Now, you can improve the output of the quality by either curating the instruction following pairs, and this is what people have followed in writing the paper less is more for alignment, or known as LEMA, where they kind of curated 1,000 instruction response set that has carefully selected examples with a lot of diversity in terms of inputs and the outputs that are obtained, and this has resulted in a lot of good performance. And another way to improve this is with reinforcement learning with human feedback, as in the case of ChatGPT. But this is a very expensive thing to do because human feedback is expensive, and ensuring that the feedback that you actually get as human is even more difficult now. So this is like a cost. It's not a cost-effective method for a lot of organizations. And when it comes to text-to-SQL, this is not even sure this is useful. Another approach that's been successful in kind of making supervised fine-tuning better is by learning or training models to imitate large language models in terms of kind of replicating the thought process of a much larger proprietary model. But there are legal implications for this. For example, when it comes to a lot of models from proprietary vendors, there are specific clauses that prohibit you from fine-tuning on the output from these models. So it's a legally gray area. And for something as straightforward as text-to-SQL, when I say straightforward, I'm not saying it's easy. When it comes to something as well-defined as text-to-SQL, there are better ways of handling this. So this is what a typical instruction following text sample looks like. So this prompt format is called the alpaca format because this is how text was arranged in fine-tuning the alpaca model, a fine-tuned llama model. This is not llama 2. This was a llama original version that was released a few months ago, which was open source but not allowed for commercial usage. The newer model is is commercially usable, which is awesome. So in our use case, the instructions will be the questions that we want answered, right? So for example, you could say something like prompt like generate the SQL for X being a question, like how many BMWs were sold in 2022, 2023, or whatever you want. And you pass the schema of the relevant tables. Schema in this case, at a rather simplistic level, just let's just say the schema is just the names of the tables and the fields. And the response will be the SQL that's generated. Ideally, you'd want a few thousand of these, and there are open commercially usable data sets that you can use for this: WikiSQL, Spider, and a number of others. And I think there's a data set on Hugging Face Hub that has around 300,000 text to SQL pairs. Before that was available, I manually curated 120,000 text to SQL commercially usable data set. So this is widely available. And also, you might want to augment this with your own domain-specific text to SQL sets if the domain is kind of arcane. For example, if you're in a regulated industry, or you're say, for example, you're in life sciences, or you're an insurance company, you might have your own type of queries that people ask, and the SQL that it generates. Sorry, the SQL that is tied to that question, and you can augment these commercially available data sets by adding those examples as well for your internal usage, of course. Now, when it comes to fine-tuning, there are multiple approaches, and this field has gone a very quick transformation in the past 3 months, even. When you start with a pre-trained model, you have a model with weights that demonstrate a statistical understanding of language. Fine-tuning is aligning this to a specific use case, as we kind of alluded to before. In full fine-tuning, you're further optimizing all the weights of the model for this task. That's instruction following, in our case, to generate SQL from text. This is not without flaws. You have this issue of catastrophic forgetting. It's a very dramatic sounding name, but the idea is that when you are fine-tuning a model for a downstream task, there's the possibility that you lose some of the things that the model has learned in the pre-training stage, which is suboptimal, especially when people ask questions in different ways. So you want the model to maintain that understanding of language in a statistical sense. Now, in partial fine-tuning, you're only fine-tuning a few layers or certain segments of certain layers, as in the case of prefix tuning and soft prompt tuning. And this has been successful in some use cases, but the one that has been most successful as of late is low rank adaptation, where you are fine-tuning a separate low rank representation of the full weight matrix. If you're not familiar with the concept of rank, you can think of rank as the number of the number of eigenvalues in a given matrix, unique eigenvalues. And the idea is that instead of having one large gigantic matrix with all the weights, you will get two smaller matrices which have much fewer parameters than the initial one had in the first place. So you're fine-tuning much less parameters in fine-tuning this model. This has proven to be very effective with some minor tweaks. These are discussed in the repo that we'll share at the end of the talk. One of the key ones that I've observed, when I was doing this work myself, is targeting, kind of getting a low rank representation of all linear layers of the transformer model instead of just the attention blocks, and that's kind of increased the training time just a little bit compared to like just the attention blocks, but it improves model performance way more. But at the same time, even with that tweak, it's much faster than fine-tuning the entire model. So it's a very effective technique if you follow the right practices. For text to insights, text to SQL is only part of the solution. You should pass the names and schema of the tables that may be relevant to synthesizing the SQL query. This names and schema tables are tables belonging to the goal layer, as we describe it in the lakehouse architecture, where we kind of we try to build a system successfully where you can run a data warehouse type of workloads on object storage. And the idea is that you want the tables which are exposed to business users to have kind of business level aggregates that can actually be useful for their downstream analytics. For this purpose, embedding table descriptions is critical, and you kind of see why, right? Like these descriptions can be either generated synthetically based on schema by a large language model, which can be reliable at some times, but for very specific domains, it can be unreliable. And the best way to do this would be like actually have a human annotating the tables manually and adding descriptions for each field. And again, you're talking about a handful of tables, so this is not a huge lift. You do it once, and I think it would be good for however long that table is used for. And I obviously prefer the latter. These embeddings, so these descriptions are strings, obviously. Then once you embed these strings, they can be indexed in a vector database, and the actual table names can be stored alongside these embeddings as table metadata. Now, what happens is when someone asks a question, the question is converted to an embedding, a text embedding, that is, or sorry, you can have a CLS token that there'll be a sentence embedding, and this embedding is used for an approximate nearest neighbor search, and the n relevant tables, most relevant tables, are returned. Here, n is low, kind of a say integer that's less than 5, and you can kind of figure out what the n should be. Essentially, when you query this vector database with the question that you ask, you want to retrieve the relevant tables, or the metadata corresponding to the relevant tables that are used to provide the context for the text to SQL model. When I say metadata in this context, if you're unfamiliar with the kind of data engineering terminology, metadata is like basically data about your data. For example, if you have data in a table, the metadata at the highest level would be the table name, the field names, and the field data types, etc. For this to be successful, you have to have your metadata stored in a single consolidated place. This could be a data catalog. There are open source ones. There are proprietary ones. There's a wide variety of such data catalogs to choose from. For the sake of this example, let's call it a metadata storage layer. On Databricks, we have Unity catalog. Again, there could be open source ones. There could be platform-specific ones. You should also make sure that the metadata indexed in the vector database is in sync with the metadata storage layer. This is critical because in generating the right SQL from text, you have to pass in the schema alongside the question in the prompt, as we kind of saw in that prompt template. The next leg of the journey is using this context. That's the relevant table schema we retrieved and passing it as the necessary context alongside the question as a prompt for the text to SQL instruction fine-tuned large language model. Again, this would be a fine-tuned decoder model, as we talked about. I've had very good results with OpenLlama 7B, fine-tuned on a few thousand text to SQL pairs with better large language models like Llama V2, MPT 7B, the newer model, and even larger models. The performance is bound to increase or improve rather. Then we can finally get the SQL by passing in the input and the right context, the question and the right context, which is the schema. Then you have the SQL. Now, this is not over yet. You have to validate the SQL, right? Because you don't know if this, like, you can have a highly accurate model, but you don't know for sure that the SQL is right or not. So then you have to validate this in a number of ways. Either you have a person who kind of sort of knows SQL as the business user, who kind of validates the SQL query and says this looks okay, or you could try this method of passing the SQL to a SQL to text model to make sure that if the explanation of the SQL roughly matches what the user asked for, then you can use a query execution engine like Apache Spark to execute this against a large table that execute this query against any kind of a table that you have access to execute queries against. This could be a really large table, or this could be a table that that is not very large, and Apache Spark works fine with either types of tables. Now, in this example, we consider Delta as the open source storage layer, where the typical business level aggregates an ad hoc query might be executed against SITs. Then you pass the results of the execution alongside the original question in a specifically designed prompt into an instruction fine-tuned general purpose LLM to get the natural language interpretation of the results. For example, if you ask the average price of a car, extended this example about BMW sold in 2023, it could be any brand of car. I'm agnostic, but instead of just saying just a number, it'll be ideal for a business user to kind of consume this if the answer is provided in a contextual manner. For example, the average price of BMW sold in 2023 was this many dollars, etc. Perhaps with some more added context so that they can kind of use it in their downstream decision-making process. It's more of a user interface and experience aspect. Now, this is the end-to-end architecture. The two key things are critical here. The first thing is that the success of the solution is 100% predicated on metadata management and syncing the vector database with the metadata. Because otherwise, no matter how good our model is, you're going to have reliability issues where you have this garbage in, garbage out problem where the business user cannot necessarily trust what you get out of the system. Then the second thing is that the quality of the data in the goal layer where the queries are executed against has to be pristine. Again, you want people to trust your system. And again, machine learning is only part of the solution. You have to think about the entire architecture. All right, now coming back to Earth, we were talking about all these cool machine learning models. This is a screenshot from the BERT SQL benchmark. It's a popular benchmark that's used to kind of gauge the performance of text-to-SQL models. And you can see that the human performance by people who know how to write SQL at an expert level, data engineers and database students, the performance is about like 93%. And with GPT-4, the state-of-the-art, proprietary model, like this is state-of-the-art overall that's available for the public, is 55%. So that's like a really big gap, almost 40%. This gap can be closed somewhat by providing even more context in fine-tuning and during query time, but it's still a really large gap to close. And even if you close it by 20%, there's still almost another 20% where the queries aren't really right. So when productionizing this type of solution, it's critical to scope and constrain the problem well. So there are a few ways of mitigating this. Again, ensuring that there's validation, and also positioning these sort of systems as data co-pilots instead of like completely replacing the need to write SQL at all. And again, the business user might have to like iterate in the validation process to see if the text to SQL matches the explanation of the query. So there are some trade-offs that have to be made. And again, instead of having like this complicated schema to kind of query against, have 2 to 3 denormalized tables, goal tables with business level aggregates to execute these queries against. I think that's a good way to start instead of like trying to kind of join a number of tables unnecessarily. Then a general guideline would be to separate compute from storage to ensure that the queries can be run efficiently. For example, using Apache Spark for execution and using Delta Lake in object storage as a storage layer. Both are completely open source projects. Then also you can improve performance of the model that's fine-tuned by adding more context in the fine-tuning process. So instead of just like column names and the table names, providing a JSONified representation of the header so that you know what the data looks like. That's one thing that you could try to do. Then finally, and most importantly, ensure metadata and data freshness is pristine, as I highlighted before. So I'll hand it over to Dillon for the last few minutes to elaborate on that last point and the data aspect of this.
Yeah, thanks, Avi. Hopefully everyone can hear me a little bit better. Now, you go to the next slide. We're going to do, you go to the next slide, Avi. Yeah, thanks. Yeah, one of the things that Avi and I talk about, Avi comes from a lot more of a sort of AI, machine learning, deep learning background. I come from more of a data architecture and ingestion and data processing background. I think one of the things that he and I completely agree on is that with the advent of everything that's happened in the AI field in the last 6 to 12 months, there is going to be a stronger need for people who can navigate between the data processing, data quality enforcement, and basically making sure that the data is fresh, up to date, reliable, and can also think in terms of machine learning. Basically like the perfect ML engineer kind of can go between both sides of those skill sets. And obviously data freshness has always been very relevant. It's been like that since the 80s and potentially even earlier, since the original data warehouses many decades ago. It's always been kind of an issue with decision support systems in general. Anytime that you're asking a question against data, you depending on the importance of the decision, it basically needs to be up to date, it needs to be fresh. But with text to with text to insights, things like that, it's just becoming more and more relevant, right? As more systems are online, they're faster. You think about AI alignment and even ethical problems, a lot of them come down to that, right? So what a lot of people usually think in the data engineering world, there's like this constant conversation around batch versus streaming. And streaming is sort of like this very niche technology. It's usually very complex. Even within people who have spent most of their careers just doing data processing, streaming is like this very niche specific thing. Usually reserved for seconds or maybe milliseconds, IoT use cases, true real-time kind of things. But what we actually find is that streaming can have all sorts of applications in terms of how it can help data freshness. And if you look at every use case, and a lot of the ones on this slide can be sort of augmented or improved by either a copilot or an LLM or something like that. They sit on this sort of general spectrum of latency. So if you go to the next slide, Avi, and go ahead and build it all the way out. It's like 6 or 7 minutes. And when you look at actually what streaming really is, this is a crash course. People, you can get very deep into this and look at all the different streaming frameworks out there. But in the general sense, streaming isn't just about latency, right? It's about the unboundedness of the data that you're processing. And if you look at it that way, you start to realize, well, there's actually all sorts of applications in the machine learning space, including text to insights, right, where the ability to unboundedly deal with data, right, where there is no, where the state is always changing, right? I never see the full picture of that data. There's incremental updates and changes happening in multiple points of that architecture. Well, streaming is actually a way to solve some of those things differently than how you might do it in this bounded world where you write a SQL query, get the response, and kind of deal with it all in batch. Right. Next slide, Avi. You can build it out for, yep. And so what we find in general is that what most businesses are looking for, and what use cases in general are looking for, is the ability to adjust that data freshness to the latency that you need, and that oftentimes actually isn't seconds, right? Sometimes you need to be able to get to seconds or maybe minutes, but oftentimes it's really about making sure that data set is up to date at the time you're querying it, regardless of the use case. Right. So go to the next slide, Abby. Before we even get into text to insights and large language models and generative AI, this is just sort of a general pattern that we see in a real-time machine learning example. So take fraud, for example. On the bottom of this architecture, when we're retraining a model, right, or if we're fine-tuning a model, right, usually we're querying all of the data from the storage, and we want to see this sort of single batch view, and that that's in a Python data frame, or maybe you're writing a SQL query and turning it into a Python data frame or something like that. But then when the application is running online, you actually want to do the exact same feature engineering, but you want to do it incrementally in an unbounded way because you want to be able to deal with it at much lower latency. Right, and so what you actually want in an online machine learning, any system, right, before we get into specific use cases, is parity between feature engineering in a stream and feature engineering in batch, right? And tools like Apache Spark, for example, actually help sort of bridge that gap. We don't have enough time to get into the details about how it works, but we just kind of appreciate that it basically will unify batch and streaming using the same API, using the same storage format, giving you the same consistency guarantees. And that makes it a lot easier when you're doing fine tuning of the model or when you're doing full retrains using the exact same features that you're scoring on in production. Also, deal with things like monitoring, right? So data drift, data quality changes over time, things that might trigger retraining the model. So go to the last slide, Avi. So if we go back again, that's fine. If you go back again to the architecture for the text to insights, you will actually see there's multiple areas where that ability to process data continuously actually becomes really relevant. Number one is just getting the metadata in sync with the embeddings, right? And that's number one. And then also number one is actually the same thing. I put both of them as number one intentionally. And on the right-hand side, when you're actually executing the query against the storage, that storage needs to be in sync with the metadata, right? So the vectorized representation of the tabular data and the tabular data itself and the metadata about them both, like that's kind of essentially the metadata is really the kind of like the link between them. Those need to be in a consistently synchronized state at all times. And number one, you have the traditional problem that all decision support systems have, which is that when you're asking the question about the data, you need to be up to date. But number two, the embedding certainly cannot be out of sync with the tabular because now you're doing a nearest neighbor search on data that's not going to be the same thing that you're fetching, because there's sort of two stages in which you're querying that data. Right. And then number two, the other area where you would want some sort of continuous processing is between the vector is from the retrieval of the information in the vector database and feeding that into the actual text to SQL generation, right? So there's kind of two stages. A lot of times people use like LangChain, for example, to compose that together. But when you're thinking about this at scale, right, you might not be using this like a single Python script to do that. What you might be doing is actually queuing those up into a Kafka topic or something like that. And then you can use a streaming framework to sort of fan that out and then process large number of embeddings. And we actually have some reference examples on our GitHub. I'm just going to show a link a little bit where we actually show doing streaming of embeddings and just all sorts of implications of things that you can do where once you start incrementally looking at embeddings, there's a whole plethora of things that are kind of unexplored territory right now where you can see how embeddings relate to each other, how they're changing over time, and you can use that number two to better answer some potential textual questions.
All right, thanks, Dillon. So one last thing, if you want to check out the code thank you everybody, first of all. But if you want to check out the code, there's the code fine-tuning the model as well as building the end-to-end architecture. So all the code is accessible with this QR code. Thank you so much.
Thanks.
All right, thank you so much to our last speakers. And after this, we have one more session as part of stage 2. That'll be up in 3 minutes. So if you need to take a break, then now's the time. Hello, everybody, and welcome to the last session of Stage 2 of the Generative AI Summit. I'm happy to welcome Afrah out of Medidata AI. Afrah is a senior data scientist at Medidata, a Dassault Systems company where she leads synthetic data solutions in clinical trials. At Medidata, her work focuses on innovative solutions to generate synthetic data evaluation, such as fidelity and privacy metrics, and new use cases for synthetic data. She has a PhD in computational biology from Cornell University and an SB in biological engineering from MIT. And with that, it'll be over to Afrah for her session, Accelerating Virtual Twins Using Generative AI in Synthetic Clinical Trial Data. Over to you.
Thank you. Let's share my screen. All right. Hi, everyone. My name is Afrah Shafquat. Today I'll be talking about how generative AI and synthetic data can accelerate virtual twins. So just for context, as you all know, and here after attending this conference and even before, generative AI is transforming this entire world where we can feel the impact across industry. In software engineering, we've seen through products like GitHub Copilot and the AWS Code Whisperer that we're now able to write code better in a more faster and agile way, where now our AI pair programmer can actually predict what we're about to write, resulting in better and more efficient code. Through AI, we are able to now document and summarize code faster. In healthcare, generative AI models are now being used to design better drugs and build better AI models for disease classification by generating and expanding training data sets through data augmentation, for example. In media, we've seen the use of text summarization, content copywriting, etc. And in art, we've all seen Mona Lisa come to life, as well as the use case of virtual photo shoots and 2D sketches to digital renderings and artwork. For this particular talk, I'm going to focus on one specific use case and use that as an example to define the importance of generative AI in healthcare. So if you focus on the use case of a business photo shoot, for example, I'm sure some of you may have already tried this, but if you haven't, this is a generative AI model that is basically able to generate business photo shoot of a customer. So for example, here I was the end user, and what I did was to send this generative AI model some photos of myself. And the prompt that I gave this model was, I want a business photo shoot wearing a white sweater or a white blouse. And as you can see, what this model was able to do was to generate synthetic photos of myself. This is a twin. This is not really me, but it's able to generate synthetic photos of myself wearing a white blouse or a white sweater. These are garments that I don't own or jewelry I don't have, but as you can see, that the model does quite well in delivering a business photo shoot given this prompt. And to really understand how this is able to do this, as most of you already know, this model has been trained on millions of photos of an image database that is accompanied by labels and descriptors corresponding to those images, so that it's actually able to learn what are eyes, what are the different facial features, as well as what does it mean when I say I want a business photo shoot versus a photo shoot on a beach or in Italy. So it's able to discern between those different prompts and is able to generate photos of an end user given those specific prompts. So if a user comes in and asks that model to generate a specific output, the model is able to do that. Now, the thing that we were really interested in was, given the example of these models, can we apply similar lessons to understanding and improving healthcare? So given the context of clinical trials, which is the domain that I work in, can we apply similar learnings to generate virtual twins and to simulate patient journeys in a clinical trial? So as you may already know, in a clinical trial, a patient goes through different phases. There is an enrollment phase, as well as a treatment phase, and a number of phases in terms of managing response, and then hopefully a recovery back home, where every single point in this patient's journey allows an opportunity for simulation so that you can design the trial design better, as well as you may be able to actually predict for every single person how a specific patient may respond to a treatment or may respond to every single specific point in the patient journey. To be able to do this, as we already saw, a generative model requires a lot of data. Now, we can do this with one patient journey, but what if we could collect 100 patient journeys? What if we could collect 3,000 patient journeys? Could we then be able to generate a generative twin of a person so that we can simulate how they would respond to a clinical treatment? To underline the importance of why this is necessary, I'm going to use the example of the CAR T-cell cancer therapy, where this particular treatment is designed for people who have really advanced cancers, and this particular treatment is it's very hard to navigate, where it requires constant treatment. It requires constant monitoring of the symptoms, such as adverse reactions, etc., such that the more prompt the treatment is, the better the end outcome may be. So given this therapy is tricky to navigate, it is really critical for physicians or for researchers to really understand how people and patients have responded to this treatment in the past, to be able to improve how these treatments are being administered currently in the present. And to give more of a perspective on why this is so critical, as you can see, if you look at the pharma companies and the clinical trial sponsors that have this data set, there are only a few sponsors that have most of the CAR T treated subjects data, where most of the companies and sponsors who are looking into testing out these therapies and designing these therapies have less than 15 CAR T treated subjects. And given this less amount of data that they have, it basically it removes the whole possibility of them being able to improve on this lack of data. So given that data is critical for innovation, and there are barriers and there is isolation of data, what can we do through this advanced technology to improve the current set of screen? Collaboration, as you may imagine, it remains quite limited due to data access restrictions, where sponsors don't really collaborate or are not able to share their data, given this data set has patient-level data. So it has restrictions in terms of patient privacy, as well as proprietary information regarding to the sponsor itself. So there are a lot of discouraging factors that limit sponsors from being able to share this data, where generative AI now provides a solution for data sharing across pharma. And if I propose a scenario, basically the scenario is, given the information is isolated within sponsors, what if we could aggregate the data and then use generative AI models to generate a clinical trial twin data set that is ready and safe to be shared? Given that the synthetic data does not have the original patient data, it will then be able to protect the patient privacy and minimize the patient privacy disclosure risk, as well as the trial sponsor non-disclosure risk. So when it comes to the question, can we create a generative AI twin of clinical trials of these patient journeys? The answer is yes, we can, through the solution of generating synthetic data, which is basically data generated through generative models. In Gartner, it's been published that by 2030, synthetic data will completely overshadow real data and AI models, where the use case goes from building instantaneous test data sets to data augmentation to being able to allowing data sharing of these sensitive data sets. Where in the news, you can see that across clinical trials, real world data, as well as the broader industry, synthetic data is creating waves. There are a number of synthetic data solutions, open source data solutions that are available. There's Microsoft Smart Noise, Gradle Synthetics, which is a Python package by Gradle, the MIT Data ZBoost, the Synthetic Data Vault, by University of Cambridge, Professor Mihela van der Schaar, SynthCity, as well as Simulants from Medidata, are all open source Python packages that people can use to create synthetic solutions and provide an opportunity for data sharing of healthcare data sets. This is an example of a synthetic data set that we created. This was published in NeurIPS as well as AMIA, where once you create a synthetic data, we have to tie it back to the initial motivation, right? The initial motivation is you want to create these synthetic data sets so that the clients who are consuming these data sets can learn from the patient journeys and are able to learn and to able to redesign their clinical trials and improve on their trial design and be able to even simulate patient outcome. So to allow that kind of iteration and modification, what you really want is for the source, for the synthetic data to be loyal to the source data, to be able to deliver similar clinical insights. To that end, what you really want is the synthetic data to be highly loyal to the source data. And here, one of the ways that you can do this is by looking at the source data in a low dimensional embedding. Here we use t-SNE. You can use PCA or any other embedding that you want, and be able to look at how does the source data look versus the synthetic data. Here, source is in blue, synthetic is in orange, and what you really want is a good degree of overlap, which would allude to that the source and synthetic data are being sampled from similar distributions. There are also other ways to look at fidelity when it comes to looking at the mean, median, and other statistical similarity metrics being offered by SD metrics, which is also a Python package within the SDV. And what you really want to see is that the univariate measures of statistical similarity are similar. So is the mean value or median value of a specific feature close to the value, the mean value of that feature in the synthetic data set or not? And if it is so, then you would have a higher confidence that that is the case, that the features are similar in both data sets. You also would want to look at the bivariate metrics, so looking at the correlations across features and seeing how well they are, how well they overlap and how well they align with between the source and the synthetic data sets, as well as another metric that we published in our papers was you can define centroids in the source data and look at the frequency of those centroids within the source as well as the synthetic data and see if there's a good degree of overlap. Tying back to the initial motivation, right? What you want the end users of these synthetic data sets is for them to derive similar clinical insights so that they can improve upon their trial design. Given that, it is extremely important that not only these overall fidelity metrics are preserved, but also the clinical trial specific metrics or the domain specific metrics. If the data sets that you're generating are, for example, in the materials industry or some other industry, what is really important are the insights that you would derive from the source data, are those preserved in the synthetic data? And as you can see that what we're showing here is a Kaplan-Meier curve where a lot of these pharma companies, what they're really interested in are the clinical endpoints. So for example, the survival probability of patients within a cohort. So what they would want to see is on y-axis, you have the survival rate, survival probability. On the x-axis, you have days treatment. So what they really want to see is the survival probability that I would get for a particular patient in a treatment cohort, is the survival probability the same in the source versus the synthetic data? And if that is so, then they would say, oh, we are able to derive similar insights and that the synthetic data set is useful and is loyal to the source data set. So as you can see here, the synthetic data sets that we created were extremely loyal to the source data, really indicating the utility of synthetic data sets in the context of data sharing, that is. There are a couple of other use cases as well when it comes to synthetic data. And I want to highlight here, I think one of the most important pieces of this. Synthetic data is like a new technology. So it's there are certain predefined use cases in the industry, but I'm going to give the example of the living heart here. And a couple of slides further, I think it's very important and critical to understand that given the newness of this technology, you have to learn how this technology fits in the explorations and the use cases that you are doing in your current job. to really figure out how this piece fits in, how it can accelerate and improve the current processes that you have. So there are fixed use cases like test data generation, data sharing, data augmentation, but there are other pieces of, there are other use cases that will be discovered in the near future and that you could discover in your jobs as well. So, but going back to this particular piece of how synthetic data can accelerate science initiatives, we are continuously looking for newer use cases and newer ways of using synthetic data. For one of our use cases, we basically looked at the Living Heart project, which is a project that I'm going to talk about in a few slides. But basically, in this project, they're using finite element models and traditional physics-based models to simulate the heart. And what really we wanted to see was, can we incorporate synthetic data and compare it to the physics-based data and really try to understand if there is a great degree of overlap. And we did see some success there, which I will talk about in a couple of slides. And then the other use case that we tested out is modeling disease progression. So one of the researchers we've been collaborating with, they were developing an ID network model, which is a multi-state model that is being used to simulate disease progression. We were able to synthesize synthetic data sets from them, from clinical data sets, where they were able to use those data sets for training their neural network model that requires a lot of data, and be able to scale the existing training data as well, which really shows how synthetic data sets can augment existing data sets and result in improved performance. So next, we're going to focus on the Living Heart project. This project is, the goal of this project is to unite researchers, cardiovascular researchers, educators from academia, from industry, and from all of these different entities, and to collaborate on really understanding and simulating how a heart would work in a real patient setting. So being able to say, okay, if this is how a heart would work, how would it respond to a certain specific medical intervention if that were to take place? And there are a number of academic institutions like MIT, LIU, BU, Stanford. There are researchers all across the world and industries that are collaborating on this project. A lot of it is open source, and you can read up on their own website. The main use cases of that they have been really exploring are a number of them, but what we are going to focus on is the mitral regurgitation use case. Here, this entire pipeline of developing the Living Heart model is quite extensive. What we're going to focus on in this particular presentation is a small piece of it. So given the current pipeline that they're using to create the virtual twin of a specific patient's heart, this requires a lot of different processes, where one of the processes is being able to take the parameters of a specific patient and using a physics-based model to expand on that parameter set and really be able to model how that the physiology of the heart. And given those data sets and our current understanding of how these physics-based models work, they're extremely computationally intensive. They're impractical to scale, as they require a lot of time. And basically creating data sets at scale from those models is completely impractical. It's not possible at all. So one of the solutions that the researchers have been exploring is, what if they can use a naive way of using Monte Carlo simulation to basically just try to sample parameters from different distributions and really and then downsample that cohort into what's physiologically possible, and then isolate certain targeted virtual patients. However, this specific process has its own redundancies, and given that the physics-based model is in practical scale, what is another alternative that we could use? Here, what we proposed was using synthetic data. So can we use synthetic data to augment the physics-based model? the physics-based data set that is generated, such that you won't need to run the physics-based model for a number of iterations, but you can use the synthetic data sets that's created based off of the physics-based data to then sample directly from that patient population rather than going through the different hoops. And the main quality of this particular process is that you don't, that by default, as synthetic data is being sampled from the distribution itself, you don't need domain expertise to filter out non-physiological patients, because the idea is that you wouldn't have non-physiologic patients outputs to filter down from. And here, what we are really able to show is that we are able to do that successfully, that the synthetic data aligns quite well with the physics-based data, that we have great alignment when it comes to the distributions of the input and output parameters, and we're able to basically propose an alternative to the traditional physics-based model through this AI-based solution that we have here. So in the end, what I really want you guys to think of is there are a number of fixed use cases. So we talked about how data sharing is critical for continued innovation in the biotech and pharma industry, how synthetic data provides a fast and secure and reliable way to share private data across pharma, as well as how synthetic data can innovate how we synthesize and augment training data sets to improve AI as well as physics-based models. And that particular last piece is not, as I would say, it's not a straightforward use case, but something that we're currently innovating on. We're currently always looking for opportunities in, and I think everyone here can basically explore how this particular solution or how generative AI can fit into their particular workflows. And lastly, I want to leave you guys with this slide that is designed by Jacob Optikar from our team, who really believes in this vision where generative AI basically can support a healthy, resilient biopharma system, just like forests rely on nutrient sharing to support a healthy local ecosystem. Biopharma relies on knowledge sharing to support a healthy, productive ecosystem for drug innovation. And through the recent technologies, we are able to provide that. We are able to provide that knowledge sharing through the most latest technologies of generative AI, and by protecting the patient privacy as well as sponsor privacy. So yeah, so that's basically it. Thank you for listening, and I hope you guys find creative ways of using synthetic data in your current workflows. Again, if you need to reach out regarding any questions, please feel free to email me or to reach me via LinkedIn. Thank you.
All right. Well, thank you very much for attending stage 2 of the Generative AI Summit. If you head on over to stage 1, which you can access from the agenda on live.summit.ai, you can check out the rest of our government policy and generative AI panel. We have a little bit longer with that. It'll be definitely interesting and a good way to wrap up our first ever Generative AI Summit. So again, thank you very much. Please head on over to stage 1 and enjoy the rest of your day. Bye now.